So it is absolutely, a great pleasure to welcome all the keynote speakers. Your work and leadership actually stand at the edge of the innovation and the transformation, where the science, engineering, and the vision converge. Today's talk isn't about the technologies that simply make things a little bit faster or smaller. We are diving into the bold stuff, the difficult part, the hard part. The kind of emerging technologies uh, don't just extend the current practices. They actually reshape lots of areas, reshape lots of fields and possibilities. And there are some innovation technologies and the ecosystems that are changing fast, like the AI, IoT, medical data science, pharma, semiconductor, among others. And all this will make huge differences for the future. And now let me share two slides with the outstanding keynote speakers and also the agenda. So today we have five outstanding keynote speakers from different universities, different areas, and also from the industry, from the venture capital. And we will have the keynotes given at the first, and then after that, there will be 40-minute panel discussion. And here it is the agenda. Since there are some kind of delay at the beginning, I think maybe at the end or during the middle, I can some kind of adjust the time a little bit. So overall, we have five keynotes, and around 10:50, we will have the panel discussion. And the overall event will take around 3.5 hours. And I also invited Nasser, who is the board chair of the IPCC conference. Now it is the 44th annual conference, so it has been several decades already. And he may introduce the conference and other insights, and then we can start the keynote.
Okay, you want me to get started, Jack?
Yeah, go ahead, please.
Okay. Hello, everybody. Thank you for all coming. My name is Nasser Ullah. I am Vice President of Architecture and Performance for MIPS Technologies. You might be familiar with MIPS as being one of the original risk companies back 40 years ago. MIPS got bought by many companies, and then 2 years ago, it got restarted as a startup. So it's a startup. But in my previous career, I spent the last 40 years working in semiconductors at Motorola and Samsung on the Galaxy phone and other things. So the things that you guys are all doing, it's very germane to us as a startup with pushing semiconductor technology to the limits. AI, biometrics, all of these things are coming in because right now what's happening in this world is we're finding out that the niche markets with technology, pushing technology is very important. There's lots of general purpose microprocessors in the world, but that is not going to make new companies money. What is happening is people are becoming more customized, looking at all the niche markets. So everything else you're doing is very good. And to add to that, thank you, IPCC, which is the International Performance Computing and Communications Conference. It was around for 40 plus years. We go all over the world. We've talked about all the different aspects and forums, and we wish to welcome you all to our conference in November. It is going to be in Austin, Texas. We'll be in Texas for a little while and then go on to Colorado and other places there. So we'd like to thank you for participating in this and thank Jack for setting it up. With that said, thank you very much. Welcome.
Okay, really thank you, Nasser, for the kind of welcome and also introduction of the conference. I think Dr. Puri is still on the way. He's in Europe. So I just wonder whether Dr. Rosen can give the keynote now. So it is a little bit earlier than your slot. I know that.
Sure, no worries. I'm happy to do so.
Okay, thank you.
Like, go ahead and share my screen.
Yeah, sure, of
It
course.
says sharing is not turned on. I've sent a request.
Oh,
Somebody
I
will
see
have to
it.
click a button,
Yeah,
and then
just
I
see
should be
that.
able to share.
Should work now.
Okay, there we go.
Uh, Before that, let me give a quick introduction of Dr. Rawson.
Please go ahead.
Yeah, sure. So Dr. Rawson is the director of the Matthews Center for Biomedical Imaging at Mass General Hospital, and one second, let me double check. Okay. And the Lawrence Lamson Robbins Professor of Radiology at Harvard Medical School. He is also the vice chair of research in the Department of Radiology at Mass General Hospital. Dr. Rawson has received numerous awards in recognition of his contributions to biomedical imaging, including the Outstanding Researcher Award from the Radiological Society of North America and the International KFG Prize. He is a fellow of the International Society for Magnetic Resonance in Medicine, a gold medal winner from RSMRM for his contributions to the field of functional neuroimaging, a fellow of the American Institute for Medical and Biological Engineering, and a member of the Institute of Medicine of the National Academies, the American Academy of Arts and Sciences, and the National Academy of Inventors. Among so many achievements, Dr. Rawson is a pioneer in the field of functional neuroimaging, like functional MRI in early 90s. Further, he has advanced the integration of functional MRI with other modalities, such as PET, MEG, and optical methods, with many tools he introduced already used by the research centers and hospitals around the world. Still, I mean, very hard to cover all amazing achievements, right? There are so many. Today, Dr. Rawson will give the keynote entitled Next Generation Brain Observatories, Advancing Neuroimaging with High-Performance MR and PET-MR Integration. As we know, the next generation brain observatories are basically changing the neuroimaging through ultra-high field MR, advanced diffusion imaging, and integrated PET-MR systems. And these technologies offer very innovative resolution and molecular sensitivity, enabling the detailed insights into brain structure, connectivity, and neurochemistry. I look forward very much to the inspiring keynote.
Thank you so much for that overly generous introduction. It's my great pleasure to be here today to try to give you a brief introduction to where I think our field of brain mapping, brain imaging is going. First, to disclose, our laboratory does get support from several of the major manufacturers, Siemens, GE, United. I do serve on the board of companies in this. And I will discuss non-FDA approved devices, and I'll say almost exclusively. I'm going to consider that a feature and not a bug of this talk. So there's a fundamental hypothesis that I'm putting forward that underlies this talk, which is that new tools lead to new discoveries. There's this very nice series of statements from Freeman Dyson, a great visionary, that new directions in science are launched by new tools much more often than new concepts. A concept-driven revolution is used to explain old things in new ways. Think of, say, general relativity by Einstein over the Newtonian gravity. However, the effect of a tool-driven revolution is to discover new things that have yet to be explained. And that is what we're driving for here, is to make new discoveries. Now, as an astronomy major in college, I will admit I have a particular affection for the stories around the history of astronomy, and none perhaps is more impactful and relevant for this talk than this fellow, Galileo, who, of course, took what at that time was a new instrument, what by today's standards, of course, is an extremely primitive telescope, but yet managed to transform our whole understanding of our place in the universe. from his understanding or imaging of sunspots on the sun that actually showed, and he could map the period of rotation of the sun, to the craters on the moon, showing it was not in any way a uniform sphere, to the multiplicity of stars in the Milky Way, rather than just a shimmering band of light. It actually consisted of millions and millions of independent stars. And perhaps his most important series of observations, the observations of the four large moons around Jupiter, the now named Galilean moons, and his observation that the motion of those moons around Jupiter recapitulated what Copernicus had been saying, that the Earth and the other planets were revolving around the sun. And to many people, this really put the last nail in the coffin of the geocentric models, moving towards the heliocentric model. He caught a little flack for this, but it was the observations that really changed our understanding of where we lived in the universe. So, of course, today there's a whole series of amazing astronomical observatories, many of them off in outer space, that give us different ways to look at the universe, all with the goal towards comprehensively understanding how the universe works. So, if these are the great observatories in space, what are our great observatories to image inner space, the workings of the human brain? No less a challenging a topic than imaging the universe. So the Hubble, of course, was the first of the great NASA's great observatories in space astrophysics. And I'll maintain that 7T MRI, 7 Tesla MRI, Tesla, of course, a measure of magnetic field strength, that's our Hubble. So here is the very first 7T MRR put in and built to be used in a clinical setting, built on a commercial clinical platform, but at this ultra high field strength. Here's the original construction, something like a small swimming pool had to be excavated. My two colleagues, Doug Kelly, and on the right, Larry Wald, the recent gold medal winner from the ISMRM, here in its very first assembly. Well, why are we so excited about high field MR? At its basics, it's because it allows us to see things that we didn't see at the lower field strengths that we more typically use clinically, 1.5 and say 3 Tesla. A great example comes from the work of one of my colleagues, Caterina Monero, who studied multiple sclerosis. Now, MS was one of those diseases that actually led to the original explosion of interest in MRI, because MRI was able to see the lesions in MS in the white matter of the brain much more clearly than the existing computed X-ray tomography that was available back at that time in the early 80s. The problem, however, is that MS is not just a disease of the white matter, but it also involves the cortex. And in fact, many of the cognitive and behavioral deficits of MS were thought to arise due to the cortical lesions. The problem, however, is that they were just not visible, certainly not robustly visible at the lower field strengths. And yet my colleague, Dr. Monero, working with others at the Martino Center, were able to show that with the additional signal to noise and spatial resolution and contrast resolution available at high field, we're able to not just see these lesions, but actually characterize them the same way a pathologist would if they had the brain in front of them and were able to put it under a microscope, showing the locations of the disease, whether it's coming down from the gray matter surface, the so-called subpeel diseases moving down from the peel surface, those arising from the white matter and moving up, or those in between. And each of these types of diseases is actually thought to arise from a different biological mechanism, and we're now exploring whether they will be sensitive to different treatments. So without the ability to see the disease, we couldn't characterize why patients were suffering, and we couldn't have a biomarker for the effects of new drugs. We now have all of these things with the advent of 7T imaging. In my own domain of functional imaging, 7T has also allowed us to explore regions of the mesoscale organization of the human brain that were only visible previously in excised tissues or optically in small animal models, and never before in humans. So, for example, my colleague Roger Tutel, who plays an important role in the development of functional imaging, before that time would do experiments of the visual system, taking brains from non-human primates, physically flattening them, taking autoradiographs to see the cortical columnar structure of the primary visual area. That's area V1 labeled here, and that's the image on the left. Today, however, with computational tools to do the flattening and with functional imaging tools like bold contrast, blood oxygen level dependent, BOLD contrast in humans, we're now able, Shaheen Nazar, one of Roger's former postdoctoral fellows, is able to see the same cortical columnar structure in vivo in human subjects. And in fact, it's not just the visual cortex where we can see this columnar structure, which frankly we've known from previous studies in non-human primates and other animal systems, but begin to explore parts of the human brain that have never been explored before at this mesoscopic resolution. Working with a psychiatrist, Daphne Holt, Roger and his colleagues began to study the columnar representation of personal space and visual space in the human parietal cortex. This, of course, was something that became very important for psychiatrists during the period of COVID, when people's vision of their own personal space, frankly, began to expand as they began to push people away from them. And what Roger and Daphne and their colleagues were able to show is that that same interdigitated columnar structure that he saw in other parts of the visual cortex were also present in the higher order areas of the brain and subserved higher order functions, such as this notion of personal space. A very important definition, and one that has great importance in the study of psychiatric diseases, where these higher order areas and notions of personal space are known to be perturbed, schizophrenia and autism being the primary example. Again, without the ability to study and visualize in individual subjects the organization of personal space, we would have no ability both to do the basic neuroscience and to explore treatments for these kind of diseases. Finally, the added signal to noise allowed us to improve the temporal resolution of functional imaging. In a simple series of experiments, my colleague Laura Lewis, John Palomini, and others began to see whether the functional responses could what temporal resolution we were able to observe in our functional responses. Unfortunately, fMRI is not directly visualizing neuronal activity. It's visualizing the hemodynamic, the brain blood flow and blood volume response to that neuronal activity. And that response is generally sluggish and was felt, frankly, to take upwards of several seconds to evolve, suggesting that the temporal resolution would be limited only to a few fraction of a hertz. And so sure enough, if you say take a simple oscillatory signal, a visual stimulus that oscillates, say, at 0.2 hertz, the fMRI signal has no trouble keeping up with it. At 3T, we could see the same at a third of a hertz. Notice, however, that the signals are now getting small, only about 0.2%. However, by half a hertz, the signals are smaller still, less than 1/10 of 1%. And it actually required high field imaging to really push this to nearer to the important temporal frequencies of slow wave oscillations. And in fact, if we push the magnetic field strength still higher, John and Laura are able to show even as high as 1 hertz, basically slow wave frequencies, the key frequencies that are present in the brain, for example, during sleep states, something not visible at lower field, was able to be seen. Notice, however, that the magnitude of the signal changes is extremely small. The y-axis here has changed as we've moved to higher frequencies, and yet still robustly visible at these high field strengths, suggesting that not only can we see the columnar level organization of the brain, but we can also follow up to slow wave frequencies, ultimately perhaps even higher in terms of the brain's response during things like sleep and other arousal state abnormalities. And in fact, Laura was able to use this high temporal resolution to look at this very interesting relationship between the coupling of electrophysiology, which he measured with EEGs simultaneously with acquiring the MR data, the hemodynamic and blood flow changes, and the changes in the cerebrospinal fluids, which are thought to, during sleep states, actually lead to an increase in waste removal, a very important contribution when abnormal to the development of Alzheimer's disease, it's thought. And in fact, was able to show here not only these oscillatory waves of activity shown in red in the hemodynamic signals, but also changes in the CSF signals, as you're seeing here in the third ventricle, time locked to that. And it's actually thought that the coupling of electrodynamics and hemodynamics is actually leading to the changes in the fluids and leading to increased waste removal, especially during periods of sleep. Finally, my colleague Zijing Dong, Fuishi Wang, and others are using this to try to quantify the direction and mapping of CSF motion during the brain, during both cardiac cycles, respiratory cycles, and during electrophysiological cycles, such as during sleep, to try to, again, better understand the relationship between electrical coupling, hemodynamic coupling, and mechanical coupling that seems to be driving waste removal in the brain. That was 15 years ago, that original scanner, out with the old and in with the next generation of scanners. Recent work with our colleague David Feinberg at Berkeley, with many colleagues from the Mass General, including Larry Wald, Jason Stockman, and others, have begun to work on the design of next generation scanners for even higher resolution human brain mapping. Well, the question that they posed is, what could you achieve if you dedicated a system specifically for imaging brain function and anatomy? Of course, most of the MRI systems that are used for research today are still general purpose clinical tools designed to image the brain, yes, but also to image shoulders, knees, livers, etc. What if you changed the design criteria and allowed you to just focus on the brain? Well, the first thing you would do is to improve the performance of the gradient system. That's the system of an MRI scanner that does the spatial encoding. It's the thing that generates that knocking sound that you've probably heard if you've ever been in an MR. And it's the key determinant to spatial resolution and temporal resolution in MR scanners. If you only need to image the brain, you can purpose-built the scanner. And Matthias David, Larry Wald, David Feinberg, and as David is fond to remind me, a lot of work from our colleagues at the Siemens Healthineers, who built the physical gradient itself and helped with the design, led to this advanced design. But it's not just the gradient system that needs to be changed. Larry and his colleagues also redesigned the RF detection system to go to a very high detection count, which can be used not only to improve the signal to noise, but also use the acceleration, because now we can do parallel acquisitions across each of these independent channels. You can see the layout of these channels here, the individual circuits, and here's the built coil, showing that we can accelerate as we go to 128 channels to a much faster imaging, and some of the images that were taken from that shown on the right. And in fact, as you can see here, I hope the next image, there we go. But I'll go back for a second just to make sure that we see the citation. David has led this effort out of Berkeley to use this scanner to really push the limits of spatial resolution here. On the left, beautiful images, so-called MR angiograms, and on the right, images of the gray matter and white matter, all taken at the very high spatial resolution and vascular sensitivity that you can get at high fields. Well, if the Hubble is our kind of general purpose and 7T serves that, how about the high energy regime? Well, the analogy may not be perfect. In astronomy, that would be X-rays. For us, high energy means ultra high performance in these gradient systems, and I'll describe for you in a moment why we would do so. So this interest to push the energetics of our gradient systems to ever higher performance was especially driven by our desire to see the connections in the brain, and I'll show you that in a second, and led to the development of our so-called connectome systems. Again, purpose-built systems. In fact, this was really the first of the purpose-built observatories, which require very high energy but allowed us to do some amazing things. So here's the kind of the working end of the Connectome, up to 22 megawatts of power. Just for a point of comparison, that's not so dissimilar to a nuclear submarine in the Los Angeles class. What are we doing with all this extra energy? Basically, what we're doing, and this was our first version, the Connectome 1.0, this would allow us to get almost an order of magnitude improvement in gradient strength over kind of conventional gradient systems. The figures of merit, the maximum gradient, and the slew rate, the change in the gradient, are shown here. This would also allow us to increase our encoding time, and thus overall, nearly a 10 times increase in the sensitivity for imaging high B-value diffusion. What do we mean by that? Measurements of diffusion or measurements of literally the Brownian motion of individual water molecules in a tissue. Why would we be interested in measuring diffusion in the brain? Well, it turns out that the brain is a heterogeneous and anisotropic media. And the result is if you can measure the motion of water molecules in the brain, you can actually infer the direction of the white matter fibers in the brain and thus map connectivity in the brain, thus the name, the Connectome. And these images were used by my colleague, Van Wadeen, one of the first to make these, actually the first to make these diffusion images of connectivity in the brain with his computational visualization colleague, Rupang Wang. He certainly was able to take beautiful pictures of the connections of the brain. And these kind of pictures are now kind of ubiquitous stand-ins for how the brain is wired. But beyond the ability to just take these beautiful pictures, of course, we're now able to use these tools to understand how the brain works in ways not only for basic science, but also for clinical applications. An example here from my colleague, Brian Edlow, a wonderful neurologist at the Mass General Hospital, actually from a time when he was at the University of Pennsylvania. I know we have speakers from that great institution now. A young gentleman that was hit by a bike, was in a coma. 14 days in, he was still completely unresponsive. And the question, of course, the family was asking, and his doctors, what are his chances of recovery? Frankly, after 14 days of non-responsiveness, the physicians felt that his chances of recovery were very modest. Physicians were questioning the family as to whether they wanted to remove life support systems. The family at that time declined, and it turned out lucky that they did. For in fact, although this patient was in a coma, in fact, a few years later, he was riding his bicycle again and doing well. Well, how is that possible? Well, of course, if you look at the image on the right of his original image at day 7, you see this large lesion. In fact, he could easily recover from this. It was this tiny lesion in the brainstem, in a particular part of the brain that controls arousal, that actually was the source of his coma and unresponsive behavior. And so the question was, could we learn, in this case, retrospectively, why he was able to recover, for indeed he did recover. So here is the day 7 image. Here were the images that we took with our Connectome and high field scanner. This is a 7T scanner. Notice the lesion here, and outlined here is a particularly small nucleus, the peduncular pontine nucleus, PPN, in the brain. And here in purple are showing the fibers that go through that structure. Notice the good, and in red is the lesion. Notice the good fortune in this case that the orientation of that lesion did transect the pedunculopontine nucleus, but not along its major path, and many of those fibers were still intact. The result was that there were plenty of fibers left to increase plasticity and allow this patient to recover. And indeed, he was able to do so, leading to the notion that ultimately, in the setting of traumatic brain injury, we will use these devices to essentially build personalized connectomes to give us a much better sense for how the recovery potential of these patients, and ultimately to guide things like surgical interventions of deep brain stimulation to try to recover those parts of the brain that may have been transected during traumatic brain injuries. Well, there we were. We had the most powerful scanner in the country. The question was, what else would we want to see? That led to my colleague Susie Huang and her colleagues, in particular Thomas Witzel, to build this next generation system, Connectome 2.0. This again, we went to a head dedicated gradient, even higher gradient performance. You can see 4 times more gradient oomph than even the gradient Connectome 1.0. Now we came up with an interesting new engineering challenge in that these gradients were so powerful that they began to generate peripheral nerve stimulation, PNS here. And so the question is, could we modify the gradient designs to still give the same MR performance and yet minimize this biological interaction? Because it turned out that the fields that generate the gradients were only a subset of the fields that led to the biological peripheral nerve stimulation. So Matthias David, a wonderful scientist now actually working on fusion engineering, magnetic confinement, and his mentor, Larry Wald at the time, actually developed a detailed model of peripheral nerve stimulation, biophysical model, and then could generate gradient designs that actually kept the MR performance, but minimized the gradient performance almost by more than a factor of 2. And that allowed the Connectome 2.0 not only to it allowed it to use its full gradient that it wasn't able to, and again see these exquisite images with much greater precision than previous studies. And my colleague now, Anastasia Yendicki, working with colleagues at Columbia, Elizabeth Hillman, and Suzanne Habert at the University of Rochester, are now putting together these incredible mesoscopic images that come from the connectome with other tools, with polarization sensitive optical coherence tomography, with tracer studies, with high resolution CT using synchrotron sources to try to allow us to understand the connections of the brain across all scales, ultimately to build an image, a map of every axon in a human brain. Probably not a 5-year adventure, maybe more like 10 to 15, but the foundational technologies seem to be there. So I see my time is running up. I'm going to have to just very briefly mention there are, of course, other things. The Space Telescope, the Spitzer Space Telescope, is looking for a chemical sensitivity in the world of medical imaging. That's PET imaging. This has been pushed to high resolution with colleagues like Rich Carson at Yale and the industrial sponsor of United Imaging in their NeuroExplorer, with images of PET scanning, molecular images that have the resolution of what was a good MRI scanner just a few years ago. Our own efforts have been to combine PET and MR because these are very complementary technologies, and in fact, with a little bit of work, can be brought together into a single scanner. This has allowed people like Marco Logio to do molecular imaging of the effects of the pandemic, not just on infected individuals, but actually showing that there's neuroinflammatory changes in non-infected individuals that has arisen due to the stress of our COVID, and seeing similar changes in molecular signals seen with magnetic resonance spectroscopy. Again, all during a single study. This might be a bit hard to describe, but again, my colleague Christine Sanders is looking to map receptor transport, a basic biological phenomena not visualized before. We're able to then map occupancy and the functional changes using MR and occupancy measured with PET. It's the combination of these two then allow us to directly measure things like receptor occupancy, something that couldn't be measured non-invasively before. And using the time domain signals, actually use this to measure internalization. So detailed kinetics and behavior of receptor systems of the brain can be measured with the combination of MR and PET together. And this has led to us, to my colleague at Chipper and Katana, to build the next generation of PET-MR scanners with a novel design, engineering design, to allow us to capture as many of the photons as possible, the spherical design. Here are all the pieces being put together. We're hoping first light will be in the next few weeks, and with a performance of well more than an order of magnitude higher sensitivity. So I think just given time, I'm probably going to need to stop here. There's lots of other things that we could talk about: movable MR, handheld MR, magnetic particle imaging, combining optically pumped magnetometer, magnetoencephalogram, OPM MEG, a little simpler, with transcranial magnetic stimulation, with MRI. All of these technologies can be brought together, lots of new ways to image the brain. And so with that, I will stop sharing, and I'm happy to take any questions. If time permits, I'll defer to the conference organizers for that. Thank you all very much for your attention.
Really, really exciting, really exciting. Yeah. I wish we have more time to get a little bit more detail, because for all the details, possibly it will take more than 1 week. Yeah. So I just wonder, any questions from the panelists first?
Yes, Dr. Rosen, I have one question. Your new techniques you're showing to show more fidelity in the brain. These machines you're talking about that shows more detail, are they more viable to get out into the broad system? And our industry is looking at them to pick them up.
Yeah, it's an excellent question. In fact, in San Diego, my colleague Art Toga and others have one of these 7 Tesla scanners. But you're right, they're not widely available. They are clinically approved. Both General Electric and Siemens now make FDA approved, 510K approved 7T devices, but they are very expensive. They're difficult to cite. And so the question is, can we, knowing what the potential is and what we're able to see, can we use things like advanced artificial intelligence, reconstruction, and image segmentation to try to see those same features at 3T? And the answer is indeed the field of lower field imaging has advanced considerably, such that there's good hope that in the future, the application of AI tools, both on the reconstruction side and on the post-reconstruction analysis side, may allow us to see much of what we could see at 7T with conventional 3T scanners. Now, the other element of things in this scanner is these high gradient performances. Again, that's also being pushed down to more conventional systems. The latest generation of systems for Siemens, for example, are pushing 200 millitesla per meter. GE now makes an FDA cleared device, their so-called Magnus, that's above 300 millitesla per meter. So one of the things that we've seen, and I think this group knows, academic sites that get to push the envelope, when the technology proves itself, it then begins to propagate and disseminate more broadly. And the hope is that these same kinds of images that we were showing will be much more broadly. This is a very active area of research. My colleague, Brian Edlow, has done a very important study on special forces, our warfighters, looking at blast injury, different than the kind of immediate concussive injury, but these continuous exposure to blasts. It's something that there were no evidence of on conventional imaging. And so sadly, these warfighters often would come back and suffer real issues, mostly psychiatric issues. And yet there was no indication of what was going wrong. And this next generation of scanners is beginning to pinpoint what, unfortunately, we were only able to see pathologically in those unfortunate warfighters who took their lives. It's tremendous advancement, a very interesting area, I agree. And please come, and happy to talk more and happy to have you visit.
Well, thank you very much, Dr. Rosen, and thank you for what you're doing to help, because this is a seriously important thing. People don't realize that until somebody gets treated TBI. This is fantastic. Your research is fantastic. Thank you. Thank you.
Thank you very much.
Great, helpful. I notice Dr. Bonnie has a question.
Yeah, thank you. Actually, you partly got answered. Thanks, Bruce. That was great. By what was already discussed. But I guess just pushing on it a bit, I was surprised initially you hadn't mentioned AI at all, but then you mentioned it in the question there, and clearly that's kind of a tool that goes back to what you said at the beginning about, how the tools drive things forward. So that's, it's clearly in imaging, that's really important. I guess what I'm interested in is your prediction for what we will be able to do, irrespective of the instrumentation, in, say, 10 years. I was particularly taken by the notion of the personal connectome, and as we get more and more into personalized medicine, we think about that a lot in various contexts, but I hadn't really thought about it that much in the context of the brain. So I'm just curious, where, if you had a crystal ball, where would we be in 10 years?
Yeah, I'm sure wherever we're going to be is not where I think it's going to be. That's the wonderful thing about our game. Having said that, there are certain things that I think we can, make decent predictions on. One is that we do know in the brain that all brains are not alike, and one of the things, especially in the behavioral illnesses, we know that there's a lot of variability in how these patients present and in their response to treatments. In other words, some treatments work very well in some patients, don't work in all in others. And the challenge is, of course, that we don't typically have the tools that allow us to distinguish those two. So there are these two collections of tools, and both of which I talked about briefly. One is this structural connectome. And as you say, I think we're at the point now where we can personalize this, and we do see important differences from individuals. And the other is the so-called functional connectome. I didn't have time to talk about it, but another way we use this functional tool is to build maps of functional connections that we can see in the correlation of the hemodynamic and thus electrical activity in the brain. And that also is quite distinct individual to individual. And people are already using both the structural and functional connectomes to, say, guide transcranial magnetic stimulation so that we can stimulate the exact part of the brain that's networked and shown to be abnormal. We're using it to guide cortical stimulation and deep brain stimulation in patients suffering from Parkinson's and other illnesses. And I think that this is something that we're really just kind of at the tip of the iceberg on. The challenge is our understanding of the fundamental mechanisms of the disease is so limited that we really need to kind of bootstrap the basic science of understanding the disease with our ability to then target therapeutics to those parts. But I think this personal connectivity, personalized medicine, especially in the setting of neuromodulation. Focused ultrasound is another neuromodulatory therapeutic target, but you need the targeting. And that's where I think the imaging tools will come in both allowing us to understand the disease in individuals and in helping physicians target using all of these new energy deposition tools that are coming online.
Thank you.
Any other question? Okay, so I have a quick question, Dr. Rawson. So actually amazing. I mean, you mentioned the future possibilities like leveraging the equipment, the hardware, software, the big data, the AI based mining, lots of technologies together will advance the field a lot, I believe. So you mentioned the 7 Tesla. I just wonder what could be the limit of the signal strength. Like if we have higher signal strength, the resolution will be higher, but also there will be the consideration from the safety. So what could be the limitations in the signal strength, and how to make the balance between the benefit and the risk?
Well, now you're making me feel bad that I was a little too wordy in the early sections, because that's in fact how I closed the discussion. In fact, there's already an 11.7 Tesla scanner that's working now in France. There have been a few built, another in Korea. There's one at the NIH. It's not working yet. We hope one day it might be. And there is a consortium in Europe now to build a 14T scanner. With luck, if the magnet works, I think the rest of the system will work, though it no doubt will be challenging. Just as you say, the real issue as you go to the higher fields is the specific absorbed radiation from the RF. I mean, those frequencies begin to approximate more like a microwave oven than they do your transistor radio. There are clever ways to work around that. Again, like this peripheral nerve stimulation and the gradients. Clever engineering and a detailed understanding of the biophysics of the interaction of these fields with the tissues does allow us to some degree to mitigate. There will be some limitations, but I'm convinced that we can operate at 14 Tesla safely. Just as you say, I think that will generate remarkable images. The signal to noise is nonlinear. It's superlinear. It's above linear, which is a good feature. So I think we've gotten hints of this at the 10 Tesla magnet in Minnesota. The France group with their 11.7 is just beginning to really bring that system online. We're super excited about that. I wish we had such a system happening in the US. Waiting for some wealthy philanthropist. If there's anybody on the line here, it's only about $100 million. Give me a call. I think they're great and really amazing things that are going to happen. And for me, the real importance of that is it allows us to kind of bridge the scales completely. The imaging folks are going, like the stalactites and stalagmites. We're working our way down from the whole brain to the mesoscale and pushing into the microscale, while the folks doing basic neuroscience have worked from synapses to neurons to groups of cells. We really want to kind of bring those together. And I think the further down we can go from the top, the more likely we are to actually create a pan-scale bridge. And that's, I think, what we're going to need if we're going to understand the brain. With at any scale we've studied, key features, key emergent features have been identified. So there's no scale that we could leave untouched if we're going to really understand the global emergent properties of how the brain works.
That sounds very, very exciting. Lots of changes, lots of possibilities in the future. That's awesome. Any question from the panelists, please?
I do have one quick question, one more question, Jack. Dr. Rosen, you said that 10T and 14T, the radiation levels become microwave kind of radiation levels, but there are techniques to take care of that.
Not quite. And in case anybody's listening and worries, we're very, very careful about that. And the FDA, of course, sets very significant heating limits. We do understand the issue, but it becomes a bigger issue the higher field you go. That is true.
Okay. That was the question. So 70 is pretty safe, right?
Yeah, it is absolutely safe. No.
Okay, good. Thank you.
I think lots of
Absolutely. Rest easy when you go in the scanner.
Yeah, because I might go to a 70 sometime soon. So
no. And I've been in many, many times myself.
I noticed Doc has a question, right? Go ahead, please.
Oh, sure. No, I'm very excited by this, Dr. Rosen, because when I was at Eli Lilly, I'm a mass spectrometrist. So I ran Eli Lilly's ion cyclotron resonance mass spectrometry lab. I had two 7 Tesla instruments, Thermo Fisher. So my question is, and of course, a lot of our collaboration was with the National High Magnetic Field Lab at Florida State with Alan Marshall's group in developing some of the prototypes. I'm wondering if you're working at all with the magnet lab at Florida State, because right now they have the 21 Tesla, world's largest ion cyclotron resonance mass spectrometer. And also they're looking for other applications in research for those. And I know a lot of this is in vitro assessment right now, but neurobiology and similar fields are an area of interest for that lab. So I'm just wondering if you have any collaborative interest or already activities in flight.
Yeah, it's a fantastic lab. I agree, and they do have a strong, biologically oriented groups that were quite aware of the work. I've visited a number of times. I'm embarrassed to say I don't think we have any active collaborations today, but we do have a new 15 Tesla magnet for mice coming, and they are the people that we would turn to learn, how to really tune the system up at those very high fields for small animals. It's a fantastic group, and as soon as our magnet arrives, which with any luck will be later this year. That's going to be a good excuse for me to take a trip to Florida, come say around February in Boston. That's a great time to go visit them down in Florida.
Thank you.
Fantastic.
Awesome.
Great.
Awesome. Okay, really thank you, Dr. Rosen, for the exciting talk and very, very helpful, very critical for the human health. I believe we look forward to the new advancement in the imaging technology for sure. Lots of content has not been covered today, but I think that is very, very good start. I believe there will be lots of communications after the event.
Fantastic. I encourage anybody to reach out, happy to answer questions or look for collaborations. We are fortunate we're hoping, fingers crossed, that we will have renewed our P41, our national resource, which allows outside users from around the country and even around the world to come and use these instruments. And so anybody interested in the 7T, the connectome, these are all part of our P41 proposal. It's the Center for Mesoscale Mapping. I guess I should have pitched that. If you just Google CMM or Center for Mesoscale Mapping, you can find it and reach out to me directly to gain access. We very much look for collaborations. It's part of our mandate, and we're, of course, very happy to do it.
Okay, awesome. I will be in Boston in fall. I will see you again there. Okay, awesome.
Thank you for the opportunity.
Okay, thank you very much for your valuable support. Yeah, thank you. I think we can go with Dr. Bonney. Dr. Bonney, if you can start. Let me give a brief introduction first. So Dr. Bonney leads a range of initiatives to encourage and facilitate the use of big data in large-scale research across the scientific and technological disciplines, with special emphasis on structural bioinformatics and systems pharmacology. He's the founding dean of the School of Data Science and professor of biomedical engineering at University of Virginia. From 2014 to 2017, Dr. Bonney was the associate director for data science at the NIH. In this role, he led the Big Data to Knowledge program, coordinating the access to and analyzing the biomedical research from across the globe and making it available to scientists and researchers. While there, he was also responsible for governance and strategic planning activities for data and knowledge management, and established multiple trainings in data science. He has done exceptional work to make biomedical research accessible as well as to advance the field of data science. Prior to his time at the NIH, Dr. Bonney spent 20 years on the faculty at the University of California, San Diego, eventually becoming the Associate Vice Chancellor for Innovation and Industrial Alliances. He is the highly respected and highly cited scholar who brings a wealth of experience to University of Virginia. And with the inspiring expertise and leadership, Dr. Bonney today will give the keynote. Technology is the easy part, which is great news because most of us have spent years pretending we understand quantum computing. Okay? But if tech is the easy part, that begs the question, what will be the hard part? Please welcome Dr. Bonney.
Thanks, Jack. I fear this is going to be slightly a downer after Bruce's talk, in the sense of how the kind of questions I've been thinking about and dealing with, both as a researcher and as a dean of a new school. So I took this quote from the iFEF statement. So, you know, I think if you adopt a unique lens, zooming on the big and tough challenges that arise to reshape tomorrow, I would say that those immediate challenges are not all technical. And we actually had a bit of a conversation about that before the meeting actually started amongst the panelists. And I'll elaborate on some of that from my perspective. So hopefully you will get to answer your question, Jack, as to what some of the challenges are. So as you just heard, and thanks for that kind introduction, I'm a computational biomedical researcher, and that's the kind of lens I look at some of these issues, these non-technical challenges. However, what I'm doing right now, of course, is much broader than that. Data science essentially covers all disciplines, but I'll focus on a few examples that are from biomedicine, but the concepts, I think the important thing to say is the concepts are generalizable. So I have like 3 different things I've been thinking about that I thought it would be worth bringing to this group. Obviously, it all starts with data, which could be a problem, and I'll get to that in a second. You cannot basically have a talk today without worrying about the elephant in the room, which is the US funding. Even if you're in other parts of the world, there's just no question that the trickle-down effect is here. And we'll talk a little about mitigation strategies. And then assuming there is funding, science is changing, and due to various technologies, and we saw the influence of that in imaging from Bruce, but I think I'll focus on how I think AI is changing some of this, but not from the explicit discoveries per se, but really from how science itself is done and what it means to be a scientist in this new era. So those are things that have been occupying my mind, and I'll try and say a little about that, and hopefully it has some relevance to this audience. I'm sure that most of you are aware of the notion of Jim Gray's putting forward the fourth paradigm, and so which relates to data. So if the first paradigm was about empirical science, the second model-based theoretical science, and the third computational science, the fourth, as he posited a little after 2000, was big data driven science. And I think these have all held up. What's I think intriguing is the time frames in which each of these occurred. The first was really took us up to the 16th century. The last one, in 50 years, we've seen unprecedented advances because of computational science. And I think the truth of it is that the data paradigm and what flows from the data paradigm is even in a shorter timescale to major fundamental changes in how we think. Whenever I mention this in a talk, it always poses the fifth question, the next question, which is what is the fifth paradigm? And I think there is, just as I posited to Bruce, what's going to be the situation in 5 to 10 years. I would say, from my point of view, the fifth paradigm is going to see, and we already heard a little about this, is the integration across scales. And in the biomedical arena, that really means everything from basic DNA all the way up to population biology, and actually putting those things together. And I'm not going to go into details of any of the kind of work that we do in this space that sort of reflects that. But it's absolutely clear to me that this is the ability to do this integration and real world evidence being applied all the way back to understanding how to treat a disease at the molecular level is happening already. There's just lots of gaps. There's lots of hurdles, particularly as it relates to the data. But a lot of those hurdles are not technical. They're cultural, about how people think about data and so on. And I'll give you a sort of example of something that I'm embroiled in right now that reflects that. But first, let me just say when you can solve the integration across scales, so many different things happen. And as someone sitting, actually having been involved in creating the first school of data science in the US at least, I'm absolutely stunned by what can be achieved when you bring researchers together who would normally never speak to each other because they're located on completely different sides of the campus. And yet when you bring them together in one entity, namely a school of data science, where data and methods are sort of the catalyst for working together, some really amazing things come out of it. And here's just one example that I would have never thought about what could happen. And it's one of my sort of poster childs for data science. So I'll just briefly mention it. I was sitting in my office one day, and this fellow, Tom Hartker, came by and said he was a physician in the emergency room. And what he noticed over time, dealing with lots of trauma, was that when someone came in, a lot of that trauma was associated with car accidents. And if indeed a person recovered, when he would talk to them afterwards, he started to develop an understanding that there was a correlation potentially between the type of accident they had, sideswipe, rear end, head on, and the type of internal injuries they had. This was important because when they entered the scanner, along the lines of what we've just heard about, occasionally patients were coming into the ER No one had an idea where to start. So they would put them in a full body scanner and they would die in the scanner. So the notion was, is there a correlation between the type of accident and the internal injury the patient has? So he, on his own cognizance as a physician, went to the Department of Motor Vehicles, which in the US is no mean feat in itself, and got public crash data and started making correlations between that data and the access he had to the electronic health record. To cut a long story short, he got stuck. He ended up getting a master's in data science in our school. And now what happens in these cases is the first responders send a photograph of the accident to the ER. So when the patient arrives, they know, based on these correlations, which have now been statistically proven, where to actually start looking for internal injuries first and hopefully treating them. So it's kind of like this wonderful data science story to me. Two very disparate sets of data, electronic health records and transport crash data, when put together by someone who's very interested and trained themselves to do this, actually made a difference to society. So that's really what we're actually trying to do here. And I would say that there's the ability to do this is under serious threat. So what is the problem? Well, the problem is that we're all reliant on the data that is out there, but there are some serious problems with this. Sorry, can you go on mute?
Yes.
Thanks.
Sorry.
No worries. Okay. So what is the problem? The problem is data is very likely to disappear. This was a problem before the latest US funding conniptions. And it was expressed in some work I did with an economist, Terry Johnson, who's in our school. This would have never happened if bringing in an economist and a biomedical researcher together would never have happened without this kind of these notions of institutions of data science. And it's really about the biological data sustainability paradox. So when you have a system where you have a certain amount of money and you're using that money to sustain a data ecosystem of some of that, as you're generating far more data from many different scales, and you're trying to curate and do other important things with that data, then there's a cost associated with that. The cost then drives down the amount of money. If the cost of that goes up, the amount of money for innovative research goes down in a cap system. The problem is, the paradox is, you need that data to do innovative research. So where does this balance lie, and what's the issues? Well, there was a worry about this before the latest US situation. And as a result of that, a number of funders worldwide formed the Global Biodata Coalition. In fact, I'm the chair of the advisory board for this. And I just came back from a meeting in Leiden yesterday, where we're now, of course, the whole problem is on steroids, because given the funding cuts that are likely to happen in US research, we're talking about a 20 to a 40% reduction in funding, which could be interpreted as potentially 20 to 40% of the data could disappear. This has catastrophic consequences, not just by virtue of a data resource disappearing. That's already happening before all of this. And there's been a lot of public efforts to try and save some of this data that have disappeared from government websites. But the issue is that you can't say, if you're sitting somewhere else in the world, well, this doesn't affect us. Well, it does, because if you look at this citation analysis with respect to what's called a set of global core biological data resources, there's a whole series of co-citations here, because effectively these data resources don't exist in isolation. They pull in data from all over the place and create integrated views. And so the moment it's not just one data resource going offline, that then it has ripple effects across the whole biological data ecosystem. And this is a serious problem. And there really is no way to address this. And I have questions for you at the end, and I'll ask you. But certainly the paper I've cited in iFEF provides a cap and trade model to address this. But the key is to implement such a model would be a total cultural change for how we think about biomedical data today, in terms of it being free and fully supplied by the federal government. This is clearly out of the window now. So new models are needed. And we're actually having a workshop later this year. If you're interested, reach out to me, because we're looking for new ideas and new thinking about dealing with this sustainability paradox. So all of this, as I said, was driven before the US funding crisis. But now that funding crisis is here, I beg the question, which you can't really ignore. It doesn't matter. I'm running a school in a public institution. But even if you're only running a lab or a private enterprise, there's just no doubt you're affected by this. So you need to have, I would argue, some mitigation strategy. And I will share with you what ours is to date. And I would be interested very much to hear what your mitigation strategies. If you haven't been thinking about it, you really need to. So the first step really is to assess your assets. What assets do you have, either in your lab or in our case within a school? Well, our assets, of course, our student workforce pipeline, which is extensive. We have 900 students now just doing our undergraduate minor, and that's without all our other programs. So there's huge number of students studying this field now. So they're assets. Our faculty are assets, they're researcher assets. And we need to figure out how to leverage those assets. And I'll say a little about that. But there's no question we're also going to have to streamline how we spend resources. And then we have to decide what to bridge. As an institution, with grants already being withdrawn and the future grants less likely, it's absolutely clear the first order of business is to bridge for our graduate students and our postdocs so that they at least can finish their training. And we need to diversify our portfolio as you do. So how we think about our 4 pillars, which are student tuition, F&A or grants, a public-private partnership, and philanthropy. We are thinking about how to diversify the portfolio more across those particular entities. And as part of that, we're actually creating a new organizational structure. So within it, we're a public university which has lots of restrictions. So what we're doing is creating the School of Data Science Solutions Initiative, which is a non-profit, which sits between our public university and the private sector and the government sectors, to actually be a broker of services, broker of our assets back and forward across this divide. So it's a model for actually moving forward in a situation where there's going to be significantly less federal funding. Having said that, that funding will also change with respect to where it's focused. And I think it's really important to keep your fingers on the pulse as to what those changes are. Clearly, AI is still going to be very prominent in the federal funding landscape in the US. However, given that you need data for AI, it's not clear how all that's going to play out. So keeping how you think about that and being ready for it, I think is really important. So, and then the last thing I'll say is really, assuming there is funding of some sort, science is changing. And I think, I actually think about some of these changes perhaps a little differently than others. And I want to exemplify that and illustrate that just with a particular example, which you probably all heard about already. And that's the AlphaFold. So AlphaFold, I think, is really an exemplar for this new generation of the way we think about science. in the world of AI. And clearly it won the Nobel Prize in chemistry for 3 folks, 2 of them from DeepMind, just last year. But if you're not familiar with the history of all of this, let me just briefly describe what the implications are for the future. So before all AlphaFold came along, many of us, my own research group included, have been working on the notion of the critical assessment of structure prediction. So at the time, the ability to predict a 3-dimensional structure of a protein from its 1-dimensional sequence was considered the holy grail of molecular biology. And over a period of like 40 years, folks have tried to address this problem. And the progress was somewhat incremental. So every 2 years, a group would get together. They would take the predictions they'd made from these 1-dimensional sequences for these structures. And then those structures would have been, unbeknownst to those participating in the competition, would have been solved. And so they could compare the the model they built against the true experimental structure. And progress was very incremental. And part of that progress that improved things is, and this is something I was involved with for 14 years, is the Protein Data Bank, which was a driver for a lot of the subsequent developments. And so here's example is the data being a driver. And the sheer amount of data that you can see grew to the point now, this is an old slide, but by 2020, when there was about 240,000 structures of varying complexity. This was raw data that actually was very instrumental in how AI was able to really address this problem. And so you can see that without going into the details here, because it's not the details of what AlphaFold, there's plenty been written, and you can certainly, if you're not overly familiar with it, you can certainly see. And I just want to highlight a few of the features that not so much the AI methodology, but the implications of the AI methodology in solving this problem. So we all knew that the result was there, but no human had actually been able to tease out those results, because you can take a protein and then it will fold into a 3-dimensional structure quite naturally. You can denature that protein and then by heating, for example, and then it will renature when under the right circumstances, when you cool it down, with nothing more than that linear sequence. So all the information needed to solve the problem of predicting a structure was in the sequence. And it was clearly, and it's why the DeepMind folks, I think, picked on this straight away, even though they were not molecular biologists, was that they knew that AI had the potential to solve this problem. And in a way, it was really, at least for AlphaFold 2, it was the transformer models that came along in 2017 were instrumental in all of this. There was another aspect where they used geometric invariance so they could translate and rotate the structure without losing information. And then there was numerical optimization with differential programming, and then overall gradient descent. So interestingly, none of this was that new when they actually cracked the problem. So there was nothing fundamentally new. Data integration was clearly critical. And these are sort of reasons why it was better than what went before. The other aspect that I think and in fact, Bruce sort of highlighted this by the number of people involved in studies around large instruments, is this was not the case in trying to predict these structures. So it was, when you think about it in hindsight, the fact that everybody was trying to compete in this space, it was small research groups all over the world were trying to come up with the solutions to the problem, but they were competing against each other and they weren't collaborating. And some more recent studies have showed that if they had collaborated earlier, they might have actually got to the same result. I think another aspect that goes, I think, somewhat underappreciated, not by this group, but certainly by some of those that are doing work in, let's say, molecular biology, is the engineering challenge is critical to this, and it's beyond most individual labs. So again, it speaks to the notion of team science. The computing power, we all struggle with this, particularly in the era of AI. We've actually written perspectives in science that show that the way the US at least operates the national labs and other computing operations is actually counterproductive in some ways, because DOE, NSF, NIH, they don't actually collaborate on any of this. They create their own silos of excellence around their own compute power. And this is in some ways detrimental, not just for computing, but also for data sharing. And then the team size, and certainly in DeepMind, was about 30 people, which is certainly beyond most labs. But they work with domain specialists. So I think the lessons that I'm bringing forth here is not that they cracked the fundamental problem in molecular biology and won the Nobel Prize for it. It's really the way that we think about doing science itself, which is really speaking about cooperation rather than competition, which of course is not the way we currently reward scientists. We don't actually we reward them as individuals, not as team members, at least in a lot of the fields that I deal with. The notion that this happens through public-private partnership, and I suspect we're going to hear more about this from the other speakers later. And then, of course, the end result of that is the translational possibilities are endless. What you can do, we went from 220,000 approximately three-dimensional structures to the order of 200 million. So that, which is all known sequences. So that has huge ramifications for all sorts of fields. Obviously, things like drug discovery come to mind, but it's also for energy production with biofuels, agricultural output, an endless array of possibilities. And it was made possible by open curated data. And going back to my first point, that is potentially starting to disappear. And the appreciation of engineering, which, if you're not in an engineering school in a university, is generally underappreciated, I would say. However, there's an interesting sidebar to all of this. We can predict a protein structure now. That is, we can run a model, we get a structure that's as good as what would have taken months experimentally, but we still don't know how a protein folds. We only know how to get to the end result. We cannot explain how that result arose. And of course, there's a whole field of explainable AI, which including many of us are involved in. But it actually changes, in some ways, the paradigm of science, in my opinion. So that if you can get an accurate result but don't know how you get it, that's very different than really the normal way that we think about science by proposing a hypothesis, testing it, and so on. This is suddenly AI has introduced a whole new way of thinking about science where the in-between steps are unknown. This is disconcerting to some people, but it seems to me it's something that we need to evolve and think about in how we're training. It also raises questions which we're involved in, and I'm not going into the research that we're doing here, but what we've done as humans for so long is to, because of the way that we think, we've actually, let's just say, we've created taxonomies to bucket things, because we can't actually, in a way an AI algorithm can, we can't look at the complete feature space that exists. Our brains just cannot do that. Whereas if you've got enough compute resource, you can do that, and enough data. So what we do is to actually put things into taxonomies. And the ones you're most familiar with is probably species taxonomies, but if you're not, there is also one for protein structure. But we've always struggled with this notion that as humans, we bucket things into these taxonomies, these protein structures, but we always come up with edge cases where something could be belong to one taxonomy, but it can also belong to another. And so in essence, it breaks down, but we live with it because that's the only way we can comprehend exactly what's going on. But what we're seeing now by exploration of feature and latent space is that, in fact, our notions of those taxonomies are probably not as correct as they should be. And this in itself then leads to a whole new set of taxonomies that enable humans to think about the problem. So there's all these kinds of developments that arise that they're really about the philosophy of science rather than the science itself. Another one of these is a notion of the human in the loop, that if a protein structure is essentially represented by a set of atoms, and each atom is represented by a set of Cartesian coordinates in a three-dimensional space. I could stare at a list of coordinates until I'm blue in the face, and I'm not going to be able to interpret it. So we've created visualizations to actually support, as humans, how we think about proteins. And the ribbon diagrams you see on the right, that's on the right is actually a snake toxin that I worked on many years ago, a postsynaptic neurotoxin. But having that visual representation enabled me and many others to actually get a sense of how this was functioning and how to design antivenoms against it. And so it's very useful, but it's also, and what I argue in this perspective, which got a fair bit of flack, I should say, is that very soon, and I teach students this, is it's very useful to have this sort of visual cue, but it's only valuable to humans. It's not valuable to AI algorithms. And they have no concept of it at all. So before long, you start thinking about a protein as if it were this kind of ribbon representation. And that, in some ways, is a curse that, although it obviously has huge value, it also has you thinking in a certain way, which actually, in some ways, given that, for example, how the motion of proteins take place, the fact that there's disorder and all sorts of other aspects, actually potentially limit one's thinking about the biology itself. And, so again, keeping all of that in mind, which seems to be very important in the philosophy of science as we move forward. So I'll stop there. These are just three sort of different caveat and things I've been thinking about. And the questions I have for you, basically, I'm always happy to have your questions, is how do we sustain the data ecosystem even before the situation we find ourselves in now? There are certainly significant questions about it, given the current culture we have in the open science culture we have in so many different fields. And second is, what's your mitigation strategy? If you feel that you are or will be affected by what's happening in US research funding, what's your mitigation strategy? And then do you buy into the notion that we should be training for a different scientific method? And if so, what are you doing about it? So I'll stop there. I've tried to give you a sense of the way I'm addressing those questions, but I'm actually much more interested in the way that you might be addressing those questions. So thanks very much.
Thank you, Dr. Floyd. Very, very inspiring talk. I just wonder, any question from our panelists?
I should stop sharing at this point, so I can figure out how to do that. There we go.
Okay. So we have a question. So what is related to the one aspect you mentioned, because you have mentioned actually a big system like the data availability and computing resource and platform and the algorithm, and also engineer effort for the whole system or for the sensor or for AI implementation, whatever. This is the engineer effort. And also lots of other aspects. I mean, it is really a systematic effort in the data science to basically effectively leverage the I would say the expertise in different areas, and then make a difference, make some application specific efforts and innovation. And I noticed you have emphasized the data. So I just curious, like what could be done, or what could change the current situation, like for the data availability. I mean, for example, if there are some key actions that can be done either from the high level or the low level, what could be those actions which can facilitate the data sharing?
Yeah, well, I mean, I think data sharing is an ingrained part of the culture of many fields, and it varies across disciplines, which I think is an interesting concept in itself, and something that we study. We have an outfit here in UVA called the Center for Open Science, which has done a lot of work in this space. But let's assume that data is open, and the issue with that is how do you solve this problem that I raised? And an example would be when I was at NIH and I was the chief data officer and associate director of NIH. I actually held a workshop of chief data officers from a number of companies, including gig economies like Uber and Airbnb. And I posed this question, how do you decide what data to throw away to sustain the system? And they looked at me like I was from another planet. And they said, we never throw one bit away. We figure out how to monetize it. And I fear, I'm not sure I fear it actually, but I think we're heading towards a situation where across science, we're going to realize that data has some monetary value. And we're going to have to actually act to receive something for the value of that data. I mean, it already is clear that, large companies, let's just pick one, OpenAI, is sucking up a lot of biomedical data and, using it in a variety of different ways. And there's no return on that to the producers of that data and the curators of that data and the whole data ecosystem. In my mind, this cannot persist. And the paper I pointed out to you actually has a cap and trade model that actually puts value on data and on services associated with data, and tries to, with the help of economists, figure out, how to make for a more balanced system. So I think that's what to me, this is a huge cultural shift. The idea that, the data has some value and we should pay for it, or we should actually expect something for the data we produce, is antithetical to the whole way we've operated until now. But I question whether this can persist in its current form, and I cannot see it unless some radical change takes place. Zach?
Yeah, very insightful, comments. And I notice Dr. Ives, please.
Thank you very much. Phil, I really loved many, many pieces of your talk. I wanted to just touch on a little bit more the sort of question of silos and data value. I guess the piece that I have seen trying to work with kind of across AI to various scientific domains tends to be there's this tension between generality and specificity. Everybody's looking at a different scope. And I think that's also often reflected in the data. I feel like one of the great challenges we have is sometimes the data is lacking in enough contextual information that if you're outside of that scope, you can actually make effective use of it. So I guess I'm wondering if, as we're thinking about sort of the value of data and kind of the case to be made for why it should be preserved or whatever, how do we take into account that aspect of it? There's often implicit parameters that nobody encodes. There's maybe things that were not captured that are actually necessary for reuse. And then there's other cases where the data is much more reusable. But it's never quite clear, at least to me as a non-expert in the data, Like, do we have strategies where we could actually kind of figure out how reusable the data is? And maybe we need kind of a science of really developing that kind of knowledge.
Yeah, that's a good question. I think in a way, data science is the science of data, and it is the field that should actually be addressing this question. I think, you know, and the problem, really the problem is, and I fully agree with what you're saying. The problem is that there really is no value placed on data.
Yeah.
You know, we're assuming all data is created equal. We're not assuming that some data is more valuable than others by virtue of the fact that it's been well curated and there's metadata and everything else. And ultimately, that it's clear, and in my own field of biomedicine, that the benefits of that were sort of reflective in the fact that these folks won the Nobel Prize. There's just no, you know, we spent 14 years building ontologies to describe that data in nauseating detail. And there's no doubt that has benefit. But the problem is, in doing that, there is no in the current economic model, there's very little reward for that. You know, you get a reward for putting a paper in Science and Nature or having a bunch of citations. You don't actually get a reward for actually producing a good data set. And that, you know, I think that's going to change. The irony of it is, just to give you an example, we wrote a paper in 2000 about the PDB. That paper, I think, now has got 45,000 citations. No one's ever read it. No one's ever read that paper because it's really a paper to reference a data set. And it's the data that has the value. The paper isn't worth a hoot. So, but, you know, we have no way, you know, the system is not set up to reward the right things in the right way in the current world of science, in my opinion. So, you know, and I also proposed a scheme when I was at NIH that we should have maybe the term wasn't quite, which got people's claw, but it was basically to have a Yelp for data. In other words, what happens so often, and I'm sure you've experienced this yourself, Zach, is you start playing with a set of data and you spend a fair amount of time before you realize that data is not going to give you what you want to give. And probably there may even be someone down the corridor in another lab who's done the same thing. And there's no way of actually commenting and critiquing a data in a sort of universal way that would be useful. And I actually see in the crisis that is now upon us that there will be these new kinds of approaches to how we think about data. You know, so maybe we should start a company together that, you know, create a Yelp for data. I don't know. But, you know, these are the crazy things that go through my mind all the time.
Those are a bunch of great points. I guess, you know, what has surprised me, frankly, is that I think a lot of us have been enthusiastic about these kinds of things, you know, build provenance systems to see how data is used, build ways of allowing for data citation, building all of these things. The underlying technologies, I think, are out there, but it's never quite seemed that there was a market, an institution, whatever it is, that's sort of committed to, let's actually build this for real, right? I don't think it would be by any means impossible to build a Yelp for data or to even build kind of a web for data citation. And again, we have a lot of theory and a lot of even mid-scale systems that can do things like tracking data usage and derivation and computational processing and so on. But to take it from the building blocks to like something a community would adopt, you know, it just feels like that has been a place where maybe the community hasn't yet been interested enough.
Yeah, you know, we started a journal in 2005, PLOS Computational Biology, and early on I wrote an editorial, is a biological database any different than a biological journal? And my conclusion was the answer was no, except in how we value them. And, you know, we value the journal article, we don't value, and you know, I think it's going to be my epitaph that's still the case. However, I do, in some way, some ironic way, the notion that we're in the process of blowing up the current system may be the only, we've been incrementally trying to get to this point of duality of value, if you like, between the knowledge derived from data and data itself. And we haven't by any means got there. But maybe it takes a blow up to actually get there. We were just talking about this at the Global Biodata Coalition, is that, this is going to be one of the chapters in the book I'm going to write when I retire, which should have been years ago, which is, there's no intelligent life down here. Because if you came from outer space and you looked at the current ecosystem we have for doing science, you would assume that there was no intelligent life down here, because you wouldn't build it the way you built it, the way it got built. It's just the historical fact that we have, many, many different silos. There are like 4,000 at least, that data resources in biology and medicine that people use quite routinely. And none of them really, one of them's, they strive to be different from each other, not the same. And, the integration of them is, hard work. So, maybe this will lead to some change. Time will tell.
So I would love to revisit this after my talk, because I think there's some really interesting trade-offs, I believe, as you try to figure out how to scope things. Like, I think part of the reason we have silos is you have to define, here's the scope of what I'm trying to do. And the problem is, at some level, we're trying to build user communities, we're trying to build communities of experts, we're trying to build general techniques, we're trying to build specific solutions. And how do you put those together? It feels like our entire mechanism for doing research really struggles with this. And, I think part of the reason we have silos is we have specific projects, and a project is an attempt to balance between general and specific. So there are parts that are sort of, provincial and personalities and so on. And then there's a piece which is, we're trying to do different things, and we don't know enough about the other things to build those bridges as well. And that is really, really hard work.
Yeah, I mean, I'm looking forward to hearing what you have to say. Maybe I should let you get on with it, and we can pick this up. It's sort of, in a way, yes, there has to be scope. And in fact, when I started to try to form a school of data science, and there was a lot of resistance to it in our university model, because it would take students away and it was financing and all the rest of it. One of the other deans, I had to convince them all that we needed a new school. And I said we would be completely different, interdisciplinary. We would be the school without walls. And he said to me, well, you can't be interdisciplinary without disciplines. And, I think that's really true. And so it's really maintaining that scope as you're describing it, to allow you to go deep, but also, as you do that, to be cognizant of the need to be broad at the same time. And I'll be interested to hear what your message is there, and we can perhaps talk about it.
I think your idea of a Yelp for data is fantastic. Maybe when I retire, I might get with you to think about that. Good idea.
Awesome discussion. Actually, Dr. Bonnie, when you mentioned the data and the engineering, actually later I will also briefly introduce my effort on one commercial. Actually, it is the commercialization effort on one product, building a system from scratch. I can feel, how difficult the engineer is, because I have been the system engineer for 2 decades. I built the sensor from scratch. Now I want to put the AI chip manufactured, and then the algorithm. Actually, this semester I offered a new course, Explainable AI. That is important for the medical application. So I just wonder, could you share some insights or suggestions about the engineering part, like what kind of engineering efforts or capability will facilitate the data science?
Yeah, so one thought that comes to mind, a little story. The many years I was in San Diego, I think a lot about engineering more from the software engineering point of view, because that's the piece that touches me most. At least it used to. It's a little different now in the School of Data Science. But when I was in a School of Pharmacy and Pharmaceutical Sciences, it was really about software engineering, and there was no respect for the people doing it. You know, even though it was absolutely critical to what we were doing. And I would laugh and say that essentially almost, you know, all the software engineers, I couldn't keep them because first of all, they could earn more money elsewhere. And second, that wasn't necessarily what was important to them. It was having the respect of their colleagues, and that was missing. So they'd all get, at that time, Google didn't have an office in San Diego. They had an office in Irvine, but they ran a bus every day from San Diego to Irvine. And I would argue that we should call it the Born Lab bus rather than the Google bus, because it was half full of my former people from my lab who were respected by us, but not the rest of the university, frankly. And, you know, I think that's been, you know, I have a whole lecture about the history of bioinformatics and computational and systems biology that sort of is reflective of that. And certainly the situation's changed, but I still don't think that we are, you know, quite where we need to be with respect to that. And of course, the landscape's changing quite dramatically with AI programming itself anyway. But I think it's, again, it comes back to a non-technical thing. It's really about a culture, and it's really about respect within that culture that that really is what's created the some of the, you know, the issues actually.
Okay. Really, thank you for the very inspiring thoughts from you. And so, any other questions? Okay, so what about we move forward to Dr. Ives? Let me give a brief introduction. Dr. Ives is the department chair and Adani President's Distinguished Professor of Computer and Information Science at the University of Pennsylvania. Dr. Ives' research interests include data integration and sharing, data provenance and trustworthiness, and machine learning systems. He is a recipient of the ASF Career Award and the alumnus of the DARPA Computer Science Study Panel and Information Science and Technology Advisory Panel. He has also been awarded the Christian R. and Mary F. Lindback Foundation Award for Distinguished Teaching and the IEEE Technical Committee on Data Engineering Education Award. And he is a fellow of the ACM. He is a co-author of the textbook Principles of Data Integration and has received a Sigma Best Paper Award, an RCDE Best Paper Running Up Award, an RCDE 2013 10-Year Most Influential Paper Award, as well as the 2017 SWSA 10-Year Award at the International Semantic Web Conference. He has served as the program co-chair and general chair for the ACM Sigma Conference and has been an associate editor for the proceedings of the VLDB Endowment and the VLDB Journal. With the outstanding expertise, Dr. Ives will give a keynote entitled Data-Driven AI for Scientific Discovery. It will help explore a transformative frontier in research, the convergence of the AI and scientific discovery. It will show how modern AI techniques are not just accelerating science, but also changing how we do science itself. Let's welcome Dr. Ives.
Thank you very much. I'm really excited to be here and really looking forward to continuing, you know, what's been a really fascinating session with a lot of discussion and thought-provoking ideas. So my talk is going to be, I think, a bit different from the previous two in the sense that I'm going to try to frame it more from a perspective kind of as a data and AI person working on a very particular set of scientific tasks and challenges that have forced us to think a lot about this kind of intersection of AI and scientific discovery. So I've sort of subtitled the talk "Work in Progress from the Front Lines." This is very much, as I'm saying, work in progress. We've identified, I think, some interesting observations, some interesting challenges that I hope will lead to some thought-provoking discussions along the way. So, of course, what I'm going to talk about is joint work with a number of colleagues. I'm going to focus particularly on the computer science AI pieces, but as we go through, I'll try to frame this also from the application domain that we're looking for. So I want to start just with the kind of high-level picture that I think a lot of us from the CS, especially kind of data integration, AI, information retrieval, we've been really enthralled with this question for many, many years, which is we would love to build AI agents and tools that hopefully never take the place of scientists and engineers, but rather help them to be much, much more efficient. We know from organizations like the Cochrane Consortium that try to collect the latest medical research on particular tasks and summarize and rank the importance, that there's a need for clinicians and practitioners and medical experts to have resources that point them at the things that they should most look at, that they should get the best lessons from, and so on. And all the time, engineers, clinicians, and so on are in pursuit of discovering promising algorithms to solve a problem or antibodies for some particular disease, or in the case of the project I'm going to talk more about, it's things like developing specific mRNA for treatments, for vaccines, for other purposes. There's a huge literature, there's a huge amount of data out there, although as Phil was pointing out, that data may be increasingly unavailable over time, but nonetheless, there's a huge amount of this data out there. It is not just in databases and data sets, it's also implicit in publications, in PDFs, in papers, in people's lab notebooks, in Google Colab, all over the place. And the question is really how to unlock it. Now, of course, if you look especially in industry, but also at places like AI2, there's been a lot of excitement and a lot of amazing progress in building large language model solutions as the AI tools for science. So whether we're talking Perplexity or AI2 has a system by Kari Asai called Open Scholar. Many of you have probably used Google's Notebook LM. All of these things actually are quite amazing at taking technical papers and giving you answers to questions and leads and other resources as you're trying to solve scientific questions. But at least we posit that that's not really enough if you're trying to build solutions. You probably don't just want your large language model to say yes or no, or synthesize this RNA. You probably want to back it up with, here's some data, here's some evidence, here's other places where it's been useful. And you probably don't just want one answer, you probably want a top 10 or something to kind of look at and process, because the goal is not that the AI solves the problem. The goal is that the AI whittles the solution space down to some starting points and candidates. So that's very much what we are excited about. And I think there's an entire community that is also interested in this. So kind of paraphrased, we want to build AI systems that give us answers with supporting evidence for all sorts of tasks. This needs to be not just from data sets and tables, which is kind of my traditional area, but also extending out into research papers and documentation and all of the other data resources out on the internet. Okay. My particular involvement in this problem has been in what I think is probably one of the most exciting projects that I have worked on. Penn has been fortunate enough to be chosen as the site for what's called an NSF BioFoundry. This is an institute that not only does research and sort of has the behaviors of a center, but actually tries to manufacture things. And so our focus is in this institute, this BioFoundry called the Air Foundry, which is kind of AI for accelerating the development, discovery, and use of RNA therapies. I think virtually everyone is familiar with the work of my collaborator, Drew Wiseman, on developing mRNA vaccines, but there's a wealth of other uses of RNA, including as guide RNA for gene therapies, including RNA like drugs that can change cell metabolism, let's say in plants or animals, which are really our target. There's a wealth of opportunities. It's very much viewed that RNA is kind of this programmable platform that you can do almost anything in, and it has the benefit that RNA therapies don't actually modify the cell itself. They affect its behavior, so there's a lot of potential benefits in terms of deploying it on a more local case. So the challenge is, it's not just a matter of creating RNAs. These are in some broader context with tasks in mind. The RNA needs to be packaged into lipid nanoparticles to be delivered to particular organs. And frankly, the community that understands how to build this kind of end-to-end solution is very small. The set of folks who even work on RNA technologies is very small. And so our goal here is not only to have these technologies for synthesizing RNA and lipid nanoparticles, but also developing AI systems to kind of grow the community, get people who have specific tasks, specific problems, to be able to harness what's going on. So it's an interesting challenge because our task is not only to sort of take open-ended questions, I want to create an RNA to increase the yield of wheat, or I want to develop some RNA therapy for coral to reduce bleaching or what have you. But there's no one answer, there's no one solution. What we really need to do is think about the fact that any answer here has to be presented in some broader context, that the RNA piece is one step in this kind of pipeline of development toward a solution. Existing published RNA are probably not what the user actually wants. They probably want a starting point that they're going to build on and modify and improve using, in our case, Bayesian optimization from other members of the team. We might not find RNA, but maybe we can find target genes. And broadly, there's a huge amount of extra information that we have to supply to the user to help them make use of whatever already exists. So our goal here is really not, chatbot style, here's a question, here's an answer, but rather, here's a question. We understand that you're on step 3 of a 6-step workflow. Here's what you might build on, here's where you're going next, and we will remember what you've done up to this point. Of course, our goal is that the ultimate endpoint is not that the user goes away, but rather the user presses a button and asks the Air Foundry to actually synthesize particular RNA and lipid nanoparticles, and then that will actually get sent to them, right? So it's a kind of microcosm, but also a special case of scientific discovery task here. I think that because we're driven by a particular use case, this actually frames it in an interesting way that gives us some additional parameters to think about rather than just building a question answering system. I also posit that this is a general problem across many scientific discovery applications. You're not just getting an answer to one question, you have a process of developing a solution. And especially if we're really talking about discovery for engineering or for therapy or whatever, there is a whole long context and there are often next steps after interacting with AI. So our particular platform here we call CARE. It's knowledge-driven AI for research. And the question that we have been working on for now a couple of years is, what should this look like? How do we balance between question answering and tasks? How do we think about going beyond what the state of the art is to actually target potential users of these technologies? Okay, so of course, we're starting with the fact that there is a huge amount of data out there that maybe even isn't directly RNA therapies, but it's building blocks toward it. There are experiments that people have run. There are public data sets on RNA, on genes, on proteins, et cetera, that might all interlink and relate. There are published results, et cetera. So a first attempt at looking at this, you might go to the solution that I think many commercial AI companies would start with, which is to say, well, why don't we just train a large language model over all of this data to give us the answers? I think over the last year and a half, 2 years, there's been a good amount of research going on in the AI community that has sort of shown that even though you can fine-tune language models and customize them, even if you ignore the challenges of hallucinations, there's kind of a fundamental problem that most language models understand a lot and can track and remember and reason about general things, but they're not especially oriented around remembering specific facts. So in essence, if you think about there being sort of a database of knowledge out there, the language model itself isn't necessarily the technology you would want to build to remember that whole database. Rather, what everyone has moved toward is what's called retrieval augmented generation, which is effectively complementing the language model with a database. The idea is large language models, even the fine-tuned ones, are great at synthesizing and summarizing facts and doing inference and finding patterns. But they're best if you can give them in the prompt, in the request, concrete information that's relevant to them answering your question. And so retrieval augmented generation involves taking all of the data that you have. Usually this has been documents, breaking the documents into paragraphs or other kind of semantic units. And now when there's a task or a question, what we do is we match the question against data in the database. We fetch a small number of most relevant results from the database. And then we ask the large language model to answer the question given, let's say, the top 10 most relevant facts from the database. And this has been spectacularly successful for many things and also has the advantage that there's a certain kind of explainability that we know which specific data items went into the prompt. And therefore, we can kind of cite those as supporting evidence for a conclusion. So today, if you use, Gemini or Bing or Perplexity or GPT, et cetera, especially the so-called custom AIs, typically this is what they're doing under the covers. It has been quite successful. And many of our friends in the NLP AI community have been investigating whether this basic architecture could be extended specifically for scientific tasks. So the folks at Future House have been building this data set called PaperQA2 with a benchmark and developing LLM-based solutions for that. And then likewise, AI2 has this really interesting open scholar effort. But again, what they're focused on is taking this kind of RAG approach, which is indexing existing content and using a language model to provide the best answers possible. We think that we need to go quite a bit further to really help scientists. In particular, scientists are going to interact with an AI tool over time. And so we should really think a lot about how to make sure that the tool knows who they are and can help with automatically, implicitly providing context so that the answers are more specific. To give an example of why we think this is important, I'm sure we've all had this experience if you go to GPT or Gemini or whatever and ask a question. So here's a simple one asking for a vector database, which is the underlying technology behind RAG. You get back this incredibly hedging answer, right? It's sort of, it depends whether you want A or B, what are your specific needs, what's your data set size, et cetera, right? Obviously, over time, a language model would benefit from having that information tracked for you already. And any AI for science, we posit, should know something about the users. In fact, it could go out to the web and collect information from the users to kind of fill in a lot of this stuff implicitly. And then, of course, there will be an ongoing discussion, history, and so on, to try to move us to a model where we have the task and contextual information, okay? A second key piece is when we get back results, it should not just be textual answers. We need benchmark data. We need links to supporting evidence, diagrams, ways of digging in deeper to understand actually what out of these results is going to be important. Okay, so these are kind of the two main things that we think we want to move toward, so that at minimum we'll have something that looks more like this, where we could answer a question where the language model already knows some amount of information about us and therefore makes a concrete recommendation rather than a generic one, and that is linked to supporting data and so on. Okay. How do we do this? Well, our philosophy, which is very much informed by kind of my own experience over multiple decades of working on problems in data integration and so on, is to posit that rather than just indexing the content in data, paragraphs and the like, what we really should be doing is indexing what we know about entities, and we should have mechanisms for annotating them, linking them, and building this broader database/index that is not only about what's raw in the papers, but extra semantic information that helps us assemble relevant answers and collect the most relevant data to help the language model give us good answers. So on the user side, we want to collect profile information, including expertise, goals, etc. Again, all of this can be pulled off the internet and done through history. Likewise, if we take a paper, we probably want to also collect information about potential authors and their expertise, and then find and maybe even derive links between papers and authors so that we can reason more transitively about the value, the credibility, the expertise, etc. And of course, we want to augment that with actual tabular data. Here, I'm just showing it from Google Scholar. We may have confidence levels, we may have provenance of where the paper came from, but also importantly, we want to be able to augment information about every data resource by analyzing it and potentially pulling out relevant information for helping us assess the thing. So maybe it's the topics and categories or methods used or credibility of authors or other kinds of information that we want to pre-compute so that we can get the most relevant answers, okay? And so now our computational challenge is the user asks a question. We need to find in this graph the most relevant entities and find ways of linking those entities together so that we can get candidate results of, we want the most credible information about this particular task. Maybe we look at papers and whether they're topical, and then we transitively look out at the author set and we look at citations and other things to figure out the most valuable versus less valuable, the most recognized versus less recognized papers, okay? So this is an on-the-fly data integration problem on a per query basis, okay? So I want to just give a little bit of a sketch of kind of the algorithmic building block to give a flavor for what this really involves, and then I'll try to pop back up to the higher level. So essentially what we do, instead of just having this kind of vector database of individual entities that gets retrieved, we have indeed a vector database, but it has links between objects and all of this other kind of related information. The goal is the LLM will query against all this data with a sketch of all the things that it wants, particular entities and matches. And essentially, we'll try to build up a table where each row represents a combination of entities and properties that's a good candidate, okay? And so we've been working actually over a number of years about how to scalably search across the combinations of different entities and assemble them into tables. The basic idea I'll try to illustrate by example. Suppose we had a very simple task of just collecting information about authors. What we might do with our sample data set here is look at the different properties or fields we have on each entity, and then try to find other entities in our index corpus that have similar properties. So we see this here. Sources A and B have at least some of the fields that we expect out of authors. B is missing orchids, and A is not telling the fields of the individuals, but this is all relevant information. So one way we can do things is add more entities or more rows from the existing data. And the other dimension, which actually adds more complexity, is that we can do what in the database world would be represented as joins. We can try to find links to other data that essentially can be used to add additional properties and characteristics. The challenge with that is sometimes, as I'm showing here, this is easy because we just look at orchid values, and if they overlap, we're good. But a lot of times these are based on approximate or probabilistic answers, and that's where you can sort of get many, many combinatorial possibilities. So when we think about all of this, eventually there's a computational problem, which is there are many different ways of combining the data. I can take my original source data just as the rows, or I can try to link it with what's in C, or I can take data set A and optionally try to find a way to get to C, or I can look at B, etc. And our challenge is usually there's an exponential number of these compared to our particular query. And now we only want the most promising ones. So what we end up having to do is create some kind of a ranking scoring function comprised of some different features from the sources and also how they compose. We will learn these over time. And the goal is to very quickly whittle down to the, let's say, 10 results that we want to feed into the prompt for the large language model. Okay. There's some certain properties like monotonicity that need to happen in this function, which I'm not going to get into detail about here, but I'm happy to talk about offline. If we do this correctly, we have an architecture that allows us to feed in all sorts of different kinds of functions for compatibility and overlap and semantic relatedness. This will consider both, again, adding rows, but also joining and linking things. The moment we join and link things, we have to think about how compatible source A and source B actually are with respect to semantic links. Okay. And the challenge computationally is we have to do this over potentially millions and millions of tables with many, many rows and columns and so on. There's a great deal of work we've done over the past, partly involving pruning. We start with the table that we're searching for. We try to figure out which fields here actually help us identify what's going on and relate to other things. We have a notion of indexing existing data through what we call data profiles, where we can, for instance, pre-compute and incrementally add to an index on, let's say, all of the tables and entities that have to do with people who have names. And so the goal is, once we know we have a name here, we go and look at the index of other people who have names. And now we kind of do reasoning about what these names are. We might have embeddings over those. And in essence, we can compare the embedding of our entry with these to understand whether they're overlapping, complementary, etc. Okay. And then we can do this over multiple attributes, so not just the names, but the orchids. And then ultimately, we have these compositional functions that allow us to say, for each result, there's a score that has to do with compatibility along each of the columns. And our goal is to efficiently scale all of this up. This is, I think, one of the most interesting active parts of the problem space. We have vector databases that allow us to compute for a single embedding a ranked list of answers. But now when you have 5, 10, 50 of these different ranked similarities, we're still working on kind of developing the best, most scalable techniques. Okay. So this core research engine allows us not to just take a query and look for paragraphs, but rather take a query, find different entities that match, and then find ways of linking them together. Right now, what we do is we take this and feed it to GPT. But the goal is to actually feed this to a custom large language model that will not just give us answers, but also show the evidence through the tabular data. Okay. Just to give a flavor for our very, very early prototype, which goes through GPT, here's an example of what we've done. We've taken basic papers. We have the language model ask what are important criteria that people would use to rank the papers. And then essentially from that, we can generate, in fact, by the LLM, a bunch of prompts. And essentially when we index a paper, we ask the language model to assess the paper with regard to each of these questions, and we pre-index it. And now when somebody asks a question, that question is expanded into matching on papers, but also, for instance, papers where we've annotated that the organism is wheat and that the authors have PhDs or MDs in plant biology and maybe that they have awards. And so now when we get a set of answers, it's based not just on matching against the content, but matching against these interpretations, these value judgments, these assessments. And we do this through this kind of link structure that I was talking about. Okay, so this is really, version 1 alpha in what we imagine to be a much longer journey. But we've already seen this makes a qualitative difference in even just the quality of the results here. Okay, we've done a bunch of work to scale this up. Our indexing techniques give us multiple orders of magnitude of speed up so that this is actually tractable. And now the question is how to really build this out. So we've been thinking a lot about how do we identify what people care about with papers for particular domains? Can we automatically generate these? How do we modify large language models and so on? But I think here's the piece that I have found in this project and elsewhere that I find to be most challenging and I'm hoping we might be able to talk about more, which is we've had in this project, and again, many others that I've been involved in, this challenge that many biomedical AI projects and data projects that I've been involved in have had to take almost a if you build it, they will come approach. We know that there's an important problem. We know that there are domain experts out there. We build a team of domain experts. We are aiming to customize AI tools for a user community who frankly does not exist yet. My colleagues, Drew and Dayon Lee, they are approached all the time by experts who know what they want to synthesize RNA and lipid nanoparticles. But our goal is to build an AI tool to take non-experts and help them to use these same technologies. And so this challenge of, okay, how do we go out, identify tasks, and somehow recruit users who aren't part of our team to help us, evaluate and train an AI with representative questions, I think is really important. We have tried to tackle AI for science in a broad way because we can get proxy questions from many domains. But I think one cannot build one general tool for all of AI or all of scientific discovery. It's a question of how to kind of drive between specific, general, known use cases, possible use cases, etc. And again, I really feel this is one of the problems at the crux of trying to get AI folks and domain experts to work on building solutions for these kind of discovery domains is we don't exactly know what the domain that we're targeting looks like because it's a user community that we are trying to build. So I hope we can have some interesting discussions about that. Recapping, I think there's huge discovery potential in this space. I think even limited tools that point us to the best resources are going to have measurable impact. But the hope is that if we really look not just at the data, but the links in the data, the credibility of the data, the kinds of criteria that people will ask questions about, we can take this much, much further. I do think we absolutely need to use data as well as AI models in this. I also think that there's a lot of work to be done in building out the data piece. I like to tell my students that Our analogy is if you were going to buy a car, you might go to Consumer Reports. Consumer Reports will have a ranking on all of the cars along multiple dimensions and a total score, and you can get what you want based on your specific needs. Can we build AI tools that can assess scientific resources in a similar way that they can capture the important dimensions and customize the results, the ranking, and so on to the task, to the expert, etc.? The key piece, I think, is actually not just on the technology side, but it's really bootstrapping the use cases that we train from, that we tailor around, that we build user interfaces around. Nurturing and building that community, I think, is really one of the key things. So thank you very much for your time and attention. Would love to discuss more about takeaways, especially in relation to a lot of the themes from the last two talks.
Insightful. Questions, please, from the panelists.
Hi, this fantastic talk, and Dr. Ive, something that resonated with me, the operative term use cases. Coming from a commercial and large company platform, and I will allude to this as well in my talk, is we, in presenting a value proposition to upper management, something that is disruptive, it can actually be transformational, game-changing. The question that we often get is, and I'm wondering with your experience with this as well, is that, hey, Doug, that looks great on a slide. I appreciate what you're conceptually proposing here. I can see how this might have impact, but show me where it's been implemented and it has tangible return on investment. And that's usually the activation energy barrier that we have a hard time getting past. So I'm wondering if one of the proposals is to get a community to build substantial use cases and have volunteer or cooperative efforts to say, hey, here was a proposal, this was generated with the tools and techniques you described, and here is the implementation with a solid and substantial output that actually resulted in return on investment for a large corporation. Of course, that's monies, that's money and that's time and that's resourcing, balance and that type of thing. So just your thoughts on that.
Thanks. Lots of great ideas there. So, I guess I should say, first of all, having done a startup a number of years ago, kind of in the scientific discovery space, I think we also very much saw this, like, what are the demonstration use cases, right? We see the promise, we see anecdotes of a couple of discoveries that have, obviously, I think many of us have seen on a personal basis, right? COVID vaccine. So it's clear that there are laudable successes. I think the question of sort of the equivalent of the market and the demonstration of the existence of the market is a very challenging one. I would say, specific to this, to our efforts with Air Foundry, right? The problem is we're essentially charged with creating that market. And again, I've been involved in a number of other projects like this where there is a circle of experts that you absolutely can get, right? But that is small, and they may not need the full generality of your AI tool because they already know what they want, right? The challenge of getting people who don't even know they want an AI tool, don't even know they want RNA, right? So for instance, one of the things that seems super exciting to me as a layperson in the RNA space is, right, there's all sorts of ways that people are combining guide RNA with CRISPR-Cas9 and Cas12 to do targeted gene therapy. And again, this is, our particular effort is really in animals and plants. It's a NSF non-human project, but all of those techniques are out there. If we build a tool for RNA, it doesn't help anyone realize that, okay, let's put RNA plus all of this other stuff, right? I think the piece that really, at least I feel we struggle with in academia, is how do you rally busy people to kind of put in time and energy towards shaping use cases that they don't yet know they need solved, right? So I wish I had a better answer for that. You know, I have more questions than I have solutions. I mean, I think we have some things we're trying. It's very much, let's start by identifying tasks, and let's start with the ones that we know we can do, and then let's start with the next set, which is stretch goals, and then try to recruit people into it and generate some success stories. And, you know, you go from simple to slightly more complicated to slightly more complicated. But still, this is hard. And I think that, for instance, many of my collaborators are trained more as scientists than as end-to-end engineers. And on my side, you know, I'm coming very much outside the domain with generic techniques. So, you know, it's a challenge. I would love to get Phil's insights as well on this, having, you know, seen things from a much broader perspective.
For sure, it is challenging.
I take that as a segue.
Yeah, go ahead, Dr. Butt.
Sorry, Jack, I overspoke you.
Okay, yeah, go ahead, please.
Yeah, fabulous, absolutely fabulous. I'm really enjoying this session. I have to say, it's all great. I mean, it's not even over yet, Doug. No pressure. But I guess the one thought and then one comment. Really. The thought was, we have a whole, I'd say 1/4 of our whole school deals with the notion of ethics, justice, policy, and law around data, and by creating a sort of personalized system, let's just call it the ethical consequences of that are not insignificant. And I'm just wondering how you think about that. Because as you were describing it, I realized, you know, me now versus me 30, 40 years ago, what my impact, you know, how it would relate to me based on what I published and all aspects of what I was doing then is very different than now. And then there's all the, you know, the convoluting factors, like, you know, I didn't stick to one thing. I've done all these, you know, these different, I keep trying to figure out what my niche is. And so, you know, there's all these different things going on. So I'm wondering about how you think about that. And then I have another question, or actually a comment about what the incentives part of what you're trying to do.
Thanks. So I guess let me start by saying there are actually just almost an unbounded number of ethical questions here, right? I mean, I think one of the first questions we had is, okay, what if somebody generates some RNA technology that, you know, whatever, it can be used as a bioweapon, or even inadvertently it gets out or whatever, right? So in fact, there are some, our existing RNA Institute, which Drew runs, already does some kinds of safety checks against these things. But of course, you know, it's a lot like computer security. You can check for a fixed number of things, but there's an infinite number of attacks. So, you know, there's challenges there for sure. Regarding ethics in terms of customization and so on, again, there's many, many issues. I will highlight one of the ones that actually I have personally wrestled with a bit, which is, you know, one of the key pieces that you're going to need here is a notion of authoritativeness. Whose data is trustworthy, etc. What are the implications if, you know, based on evidence and what other people have said and so on, you downrank some particular investigator? You know, that could actually be highly detrimental to their career, and maybe it's not a fair assessment or whatever, right? So there's a lot of these kinds of things that get very, very complicated. I will also say, and maybe this connects a little bit to your comment, Phil, about having worked in different areas. Over the last 25 years, what I have personally found is by building some general ranking or general structure or general schema or general ontology, we are often making something that loses a huge amount of the context in this. So in essence, I'm more and more and more a believer in kind of query time ranking because it takes context into account, right? So rather than giving an authoritaveness score to a person, we might be giving a relevance score to the impact of a particular work in this particular space relevant to this particular user. And now the question is, how do we learn, something useful there? I think in reality, for a long time, there's going to be almost an unbounded number of questions where we will just have to kind of start with the defaults and just look at the evidence and have some default thing that isn't particularly up-ranking or down-ranking any individuals or what have you. But these kinds of problems get very challenging. We also have this question of, when is it that users' queries and users' data and past, let's say, failed experiments, or even just the second best candidate for some RNA therapy that isn't manufactured, when do we get to use those to train a general purpose AI, right? Our solution right now, according to the terms of the grant, is, when we have commercial folks who do this, we're going to have kind of a moratorium, and then after that, we can at least train the AI on them. And I think that's a pretty fair way of doing things, especially, I think we all have this sense that there's the published scientific literature is basically missing all the second best cases, all the failed cases, all the things that weren't interesting enough to publish about. We would love to build AI models that include all of that stuff, even if it wasn't interesting to a human. So I don't know if that directly touches.
I mean, I think at the end of the day, the gain will outweigh the pain of the ethical consequences. And the way to do that, in my mind at least, is to always remain transparent about exactly what you're doing, and that goes a long way. The thought I had about creating the audience, creating the user base is, I don't have a good answer, but there are people, I don't know if you're interacting with them, who study the science of science, and they study the incentives that drive scientists to do things. And I think those kind of conversations will be very useful. Because it's not, there are different incentives out there for different communities and different purposes. I mean, the kind of thing that comes to my mind, of course, is just like running competitions and things, and which incentivizes people to work around the clock. But I don't know. But I mean, certainly, if you don't have contact with those kind of folks, I've been working with some of those, and I'd be happy to put you in contact. And I know they'd love to talk about this sort of thing.
Look, I'm always delighted to talk to more people about this. I mean, I think, again, this has been one of the key challenges that I've seen in many of these projects. I remember being on some of these open science workshops where it's like you discover there's 50 or 60 of these different data portals, and everybody's like, see, we have this amazing thing. Why does nobody know about this? I feel the more we can think strategically about that, the better. I do remember a decade ago, we had some success by doing things like Kaggle competitions and so on. And I'm imagining many of our, at least universities these days, because of the interest in data science, may have, forums and mechanisms where we could do a one-day, hackathon or whatever. So some of these things work at an organic, small level. And maybe that's the bootstrap, but I still feel this is in my mind, one of the great challenges and weaknesses here is it's hard enough to get domain experts in AI and domain experts in science together. Now, how do we get the users onto that team as well?
Yeah, I don't have any answers, but I'm thinking that we are at an unprecedented moment in history when there's going to be a whole bunch of people who are going to be out there looking for something to do, who have a lot of expertise. And I'm just wondering whether somehow that can be tapped.
Very, very awesome discussion. So Dr. Ives, so actually, the big data and this kind of system or this kind of application is really complicated, right? Like if we consider the heterogeneous nature of the data and also the hidden relationships among the data, and I just wonder what is your thought or insight about, the new idea discovery or, some kind of really breakthrough in the scientific research? I mean, whether this kind of, large knowledge model or language model can facilitate the scientific research.
So I think lots of great underlying questions to that. Let me start with one of the things that I've been kind of personally overjoyed about, having worked on data integration tools for 3 decades now, or almost 3 decades now. 5 years ago, we could look at trying to tackle these problems through a combination of, like, we build a general tool and then we say there's a special plugin that takes into account, we're doing gene sequence matching instead of name matching. It was extremely difficult to think about end-to-end solutions when you build stuff and then a human is here, and you build stuff and a human is here, and you build stuff and a human is here. Not to mention that, like, actually taking all this and deploying it into real production, you need very complicated teams. Today, language models can cover a huge number of those applications. They know this is gene data. They know what the right function is to match these things. So that has been transformative. Like, I like to think we've moved a lot of things from human in the loop to LLM in the loop. And so obviously we go from, like, semi-automated to almost fully automated for those kinds of things. That is not to say that we don't need humans at the end to vet what we're doing, right? This is the same as vibe coding or any of these other things. You cannot just plug and play and it just goes, right? The other big thing is, I think embeddings have really opened the door to a lot of interesting things. So among other things, it means you can build in image similarity, text similarity, video similar, like whatever you want. There's a generic thing that, okay, we have an embedding here, we have an embedding here, and we have some metric. That allows us to regularize a lot of tasks that before were go find some algorithm and plug it in here. So I think this means we can automate much, much more. I don't know exactly where the most fruitful things are, but I'm actually quite confident that just putting all of the stuff up in a more regularized way. And again, I think the key is linking different pieces and supporting with evidence. I don't think just giving answers is enough. I do think this is the direction that's going to have some measurable impact. I'm not promising it'll be Air Foundry that will do that. I hope so, but I think that there's vast potential here because we've moved from things that were one-off, human in the loop, somebody hacks something together, to now stuff is automated end to end. And just, the same way that people are now productive with coding, even though all of the vibe coding things are only semi-reliable, I suspect we're going to see a lot of cases where even if you whittle down what you need to read from 1,000 papers to 50 papers, that's a huge benefit. I will say my own experience as a collaborator across disciplines here has been hugely different from some of my past projects because I can ask deep research. What are the ways people are doing things in the RNA space? What are the applications, right? Just being able to get that high-level roadmap is huge. So I think we're already on the cusp of this. The main question is, how far will it take us?
Yeah, absolutely. I believe, the embeddings you mentioned, they can basically reflect the similarity by its learning capability for sure. Oh, I noticed Dr. Curie is here. Maybe I made some mistake. Sorry about that. Possibly when I sent out the email, I did not change the time to you. So really, really sorry. But we have the YouTube channel. I will send you the link shortly so everyone can see the the whole event. I will share the YouTube link later. So we have,
Thank you.
Yeah, sure. Dr. Curie is from University of Milan and has, awesome leadership in Archivo-E. Yeah, so we just we just finished the talk from Dr. Ives. So before we possibly move forward to Dr. Puri, I just want to double check whether there are some questions still for Dr. Ives. Okay, okay, cool. Then Dr. Lars, how about we move forward to Dr. Puri, and then you'll give the talk, and then after that I will give a brief talk about my work and the commercialization effort. Really, thank you. Dr. Puri, I will give a brief introduction. So Dr. Puri, yeah, go ahead. Sure. Dr. Puri is a full professor of computer engineering with the University of Milan. He has been the visiting professor and honorable professor at around 10 universities all over the world. His research interest includes AI, IoT, cloud computing, among so many, and has published more than 400 articles. Dr. Puri has received numerous recognitions and honors and offers leadership and expertise broadly to IEEE and all over the world. He is a fellow of the IEEE, a fellow of iFIP, distinguished scientist of ACM, and a senior member of the RNNS. He has been the IEEE Region 8 Director in 2023 to 2024, IEEE VP for the technical activities in 2015, IEEE Director, President of the IEEE System Council, President of the IEEE Computational Intelligence Society, VP for Education of the IEEE Biometrics Council, VP for Publications of the IEEE Instrumentation and Measurement Society and the IEEE Systems Council, and VP for Membership of the IEEE Computational Intelligence Society. He also served or serves as editor-in-chief and associate editor for around 10 IEEE transactions and journals. I really hope I have more time to cover everything, but Dr. Puri's achievements are so many, really fantastic. Today, Dr. Puri will give the keynote entitled Artificial Intelligence in Cloud, Fog, Edge Computing, and IoT. The cloud, fog, edge, and IoT infrastructures grow in complexity, and they require advanced components and intelligent management techniques to remain efficient. Adaptivity and autonomous learning are key to enable the dynamic configuration and optimization, especially for non-experts. Given these complex systems and the grand challenges, please join me to welcome and thank Dr. Puri to share his insights today.
Thank you, Xinzue. Apology for the misunderstanding about the schedule. Today is really a great pleasure to be with you and have a look to what we can do to manage the modern architecture based on cloud as well as fog and edge computing and the use of the Internet of Things in this kind of architecture. This distributed architecture, which are nowadays the most common structure to put together the various components at the edge, but still have in a central repository the main data and the main applications, create a hierarchical structure in which we have at the peripherals the Internet of Things component, the opportunity to connect some simple devices, some simple peripherals to the network, but still offering the opportunity to transfer many data and receive many commands from a more complex application, especially based on artificial intelligence, which can reside in the cloud, or if we wanted to limit the amount of data that are transferred, that can be placed in the fog or even much nearer to the peripherals. Artificial intelligence is really useful in this type of architecture to support the modern application, really in a broad variety of cases. To build the applications, we have nowadays various tools which are made available by many companies, so that even people who are not really expert of this technology, of the details, of the internal details of these techniques can actually benefit from them, even if they may not be able to exploit fully their capabilities. In order to build the applications, we can also find on the market several components, several services that we can glue together in our application, picking the ones which are most effective for our own specific case, starting from the collection and the analysis of the data from the peripherals, moving up to the extraction of the knowledge from the data collected from the peripheral, and for example, by machine learning, by different type of artificial intelligence techniques. We can have also specific services focusing on specific activities that are typical in the modern application of artificial intelligence. And we can have also component services that allow to build the user interface in a much more flexible and natural, from the point of view of the humans, way. So that we can use not only the traditional graphic interfaces, but also touch, also vision, also the voice, so that really it will be much more natural. And on the market, we find also opportunity in which we have not only these basic components, but we have services which are implementing more complex use cases, putting together various artificial intelligence services for a specific type of use. And some companies have made available also verticals in which we have not only one specific use case, but also the chain of all cases that are useful to implement, for example, modern manufacturing systems or healthcare system without the need of selecting and connecting the various components. And we have also on the market data mining and knowledge extraction tools up to the comprehensive data analytics systems, where the various components, the various services from the collection of the heterogeneous data, from the storing of the heterogeneous data in appropriate type of repository, and the analysis, the extraction of the data, the creation of specific views for the user are available. And we, among the possible presentation of the data, we have visualization tools, so that is much easier for the human to understand the information, the knowledge contained in the data. And we have also monitoring tools, so that events occurring in the environment can trigger through the data the attention of the users, of the operators, and as a consequence, be more efficient in managing possible critical cases. Finally, we have also decision support systems which are able to analyze the data, create compact views, extract the relevant knowledge, and as a consequence, provide the support to the decision makers to take more informed decisions. But the artificial intelligence can be used also to manage this type of distributed infrastructure, the cloud fog edge model, as well as the connection of the Internet of Things portion. And there are many, many opportunities in the entire set of activities. For example, when we wanted to use a cloud fog service, we need to specify a service level agreement so that the service provider can actually see what we need and provide the most appropriate opportunities. Or we need to, in a multi-cloud environment, we may need to select the specific cloud that we want to use, or we may need to distribute our parts of our application in the various clouds selecting the ones which is more efficient for each specific component. In all these cases, artificial intelligence has been shown very effective in optimizing the selection, in supporting the mapping. In particular, fuzzy systems has been studied and is available on the market to specify the preferences, the characteristics of the service, and as a consequence, the kind of need that we want to have from the cloud infrastructure. And neural networks, as well as the evolutionary computing, has been shown effective to perform the optimization, to perform the mapping of the needs on the specific cloud services, on the specific virtual machines that we have in the architecture. And machine learning has been shown effective, different type of approaches has been shown effective in order to extract the knowledge from the previous cases so that the cloud provider can best offer solutions to the customers, looking in the details in the service level agreement and having the experience of various other users as a base to select the most appropriate offer, including the specific user who may have some specific needs different from the ones of the other users. Of course, if the user is specifically continuously using the same type of service provider. In the case of distributed architecture, like the one that we have in the multi-cloud or in the cloud federation, we need also to distribute the various components. In the multi-cloud is the responsibility of the designer of the application to split and perform the allocation. In the cloud federation is the central blocker of the cloud federation, which is responsible to perform the distribution according to the most appropriate mapping and the specification of the preferences and the needs of the user. And this may include a multi-objective allocation, considering, for example, the prices, the type of services, the performance, the quality, and so on. For this reason, the evolutionary computing has been shown effective for the multi-objective optimization as well as the many objective optimization. But then, as I said before, we may need to put together different services. For this purpose, also the selection of the services can be based on the fuzzy system definition of the preferences, and the matching has been shown effective in various experiments in the literature and in some implementation in the market by using both neural network and evolutionary computing. And also in this case, the machine learning can be useful to extract the knowledge from the previous cases and help in guiding the mapping. Resource management, the allocation of the various resources to the task is important, as well as the allocation of the tasks on the virtual machine and the virtual machines in the cloud infrastructure. Also, this type of operations, this various type of mapping, basically require the definition of the characteristics of the resources that we need, and and as a consequence, it's important to use the fuzzy systems also in this case. The essential role of the fuzzy system in all the various type of definition of the specification we have seen is essentially related to the fact that this simplifies the life to customers, which may not be so used to the infrastructure, to the architectural infrastructure, and as a consequence, they may not be really aware about the numbers that need to be requested for the performance, for the memory, and for the other resources. But they may give a definition of their needs in terms of words. and as a consequence, it's important for the service provider to have an understanding of the natural language in order to extract what the customer really mean with for example, large memory or small memory, so that it can perform the appropriate mapping. And evolutionary computing has been shown effective also in this case as a tool for the optimization of the mapping. When we wanted to run the various applications on the node of a complex architecture, actually we wanted to have the ability to ensure the best performances in the infrastructure for the benefit of the various applications. But if we overload one of the nodes or some of the nodes, the performance of the tasks running on these nodes may be reduced. And even if it is satisfying the minimum requirement specified by the user, may not be so appealing. As a consequence, what we can do? Well, we can use artificial intelligence, for example, neural network and fuzzy system, to predict the behavior of the tasks, and as a consequence, to understand if a task is not performing as we wish, and we may need to consider moving somewhere else the task. Or we can look overall to the behavior of the various tasks running on a node. We may need to predict the overall workload of the node so that we never reach a situation in which such a node is really overloaded. When this occurs, we can consider moving the tasks on other nodes. We may need to perform a dynamic reallocation of the tasks. If we are not able to predict in advance when we are going in this critical situation, we can allow the system to enter in this critical situation, and we can consider the use of neural network, for example, for detecting the overload. And that will trigger the task to perform the dynamic reallocation in the system in order to reduce the overload of the nodes which are in a critical situation. And evolutionary computing, obviously, is effective to perform the new optimized allocation. Similarly, in Internet of Things, we may exploit the benefit of artificial intelligence to perform the allocation of the resources to the various tasks, as well as to perform the dynamic reallocation. And fuzzy systems, also in the case of the Internet of Things management, has been shown effective to specify in a more natural language the needs, the preferences, possible constraints of the users and the specific application. On the other side, neural network has been shown effective to perform the mapping in some simple cases of the resources to the tasks. And in general, evolutionary computing is effective for the multi-objective optimization when we want to consider price, performances, communication cost, and other type of objectives, as well as constraints. Also, in the case of the Internet of Things, we can consider the performance prediction and in order to adjust the allocation of the resources and perform, as a consequence, the balancing of the allocation of the tasks, if possible, if they do not need to be strictly allocated on one specific node. Another very important aspect in this modern infrastructure is the energy management. Energy is a really critical resource for tourism. Energy as a cost. If we are able to reduce the energy, we are able to reduce the cost of running the entire infrastructure, and as a consequence, we can offer a cost reduction to the users, attracting many more users. On the other side, to produce the energy, we actually need to use natural resources which may impact the environment. And as a consequence, if we can reduce the amount of pollutants that we are generating in order to produce the energy, we will have definitely an advantage for the environment, so that we can leave a better environment not only for us, but also for the future generations. Managing the energy implies that we need to predict the use of the energy in the various nodes, and as a consequence, think how we can improve the overall energy usage. For example, by reallocating some tasks without impacting the performances, but being able to reduce the energy that we use. Neural network and fuzzy system have been shown very effective for the prediction, as well as for the machine learning, for extracting the knowledge from the previous cases so that we can have a better analysis and management of the possible allocation guided by the use or the reduction better of the energy. When we design a complex infrastructure like this, we will need to consider that redundancy in the infrastructure is important to ensure the continuity and we need of the service, and we need to ensure also the energy minimization, the cost minimization, and the performances. And for this, also there are various aspects of artificial intelligence which have been shown effective. But fault may occur in all this kind of infrastructure, both cloud, fog, edge, as well as in the Internet of Things. So when a fault occurs, we may need to move the computation on other nodes in the infrastructure in order to provide the continuity of the service. We can do the reaction to a fault in order to ensure the resilience of the system, but we also can act in advance. We can, in several cases, predict with sufficient advance the possible occurrence of faults. And this is feasible in many types of architecture when enough knowledge is available. The neural network, the fuzzy systems, as well as the machine learning, has been shown effective for the prediction, for learning from the experience when the typical components that we have in our system may become faulty. Another important aspect that we need to consider is security. In particular, we do want to have the ability in this kind of complex infrastructure, especially when the application is critical, we need to detect the presence of intrusion or the malware, and then we may need to be able to manage the trust to ensure the trustability of the various parts of the architecture in order to deploy in this part the tasks which require a significant level of trust with respect to the security. Neural network and fuzzy systems have been shown effective to perform the classification, the clustering of the security pattern, and some statistical machine learning has been shown really useful also in this perspective. And they have been shown effective also to perform the analysis of the trust, and as a consequence, the classification of the trust of the various components, so that we can act in the allocation, having also this information to protect our applications. So the analysis of the threat, the security prediction of the various parts of the infrastructure is really important to manage as best as possible the applications, the data, which are mission critical. And for this, the artificial intelligence has been shown effective in detecting, in performing the analysis, as well as in predicting the security level. There are two other aspects that I would like to point you out. Monitoring is an important activity in ensuring that these complex infrastructure are properly managed. We have many sources of information, sometimes too much, and as a consequence, the operators may not be able to really understand and capture what is happening in the infrastructure due to the amount of data, due to the amount of information they need to look at. What we can do? We need definitely to have monitoring tools which filter the information coming from the various sources, from the various components and tasks that we have to understand the behavior of the system in order to trigger the attention of the operator on the critical aspects. For this, it has been shown effective not only the use of traditional algorithmic approaches, but also the use of artificial intelligence so that we can specify with fuzzy systems the characteristic, the behavior that need attention, the possible constraints, and with neural network and machine learning, we can build tools to detect the critical situation, to detect the behavior and the anomalies that we observe in the system, and eventually to predict them. The last aspect is a price. The use of this kind of infrastructure is critical from the point of view of the price, since we do want to have the lowest price as possible in order to attract many more customers. On the other side, we need to have enough revenues and enough surplus for the service provider so that the service provider can perform the best maintenance, can expand the services offered in the system. But they also need to have a remuneration of the initial investment. How we balance these conflicting goals? Well, neural network and fuzzy systems and some statistical machine learning have been shown very useful in order to predict the trends of the cost and the user demand on the market and to perform the best optimization so that we can have happy customers, and on the other side, the providers may have enough surplus to reinvest in the system. So the contribution of this very brief talk is essentially related to the fact that I like to point out that we are aware that more and more we need intelligence in the applications, but we need intelligence also in the management. And artificial intelligence, the sub-symbolic computational, the sub-symbolic artificial intelligence, in particular, which is known also as computational intelligence, has been shown effective in both cases to build more effective, adaptable, evolvable applications for many applications, especially when we need to deal with the monitoring and control of systems for medical applications, for various type of signal and image analysis that we may find, for example, in automotive, in manufacturing, in embedded systems, in entertainment, in medical applications, and so on. But artificial intelligence has been shown effective also to manage this infrastructure, providing the flexibility, the adaptability, the capability of learning from the previous experiences, which is often difficult to be captured in an easy way by using an algorithmic approach or a conventional statistical approach. Thank you for your kind attention, and if you have any question, I will really be happy to answer.
Yeah, sure. Dr. Pure is really excited for sharing. Any questions from our panelists, please? Okay, Dr. Pure, I really like the talk. So as you mentioned, the massive devices will be everywhere. Actually, the scale is growing very fast, like the smart factory, autonomous driving, and medical applications. So considering the device usually has limited resource, like the battery or the computing resource, so possibly, or I believe, the algorithm you introduced is possibly deployed on both cloud and edge, right? So the edge does not need to handle all the algorithms. So I believe the server or the cloud can handle some kind of calculations, right?
You're right. Actually, on the edge, we can use some artificial intelligence techniques, maybe not have the very complex tools with the learning part, but when we have been able to create some specific solutions that have been configured by using, for example, by using a deep learning structure or a more simple neural network, we can put it on the edge in many cases if there is at least some computational complexity in order to perform the very preliminary tasks that can be useful, for example, to reduce the amount of data that need to be transferred to a more complex operation. For example, if an application we are interested in just to detect peaks in a signals or some variation in an image, this is the part that in general can be performed locally on the peripherals, and only the presence of the trigger can be forwarded to the fog or even to the cloud, where we have the most complex part of the application using this data, learning and taking the more complex decision on the activities that we need to carry out at the peripheral. So nowadays, distributing at the various level the computation, the parts that needs to have sufficient computational capability or storage, moving them more toward the clouds and leaving what need a limited amount of resources on the peripheral to reduce the to reduce the communication complexity due to the massive data that the peripherals are typically producing. This is the typical strategy that is used nowadays in a broad variety of applications.
For sure. This is really helpful. As you mentioned, the edge, fog, and cloud, they actually work in the whole system. It's like end-to-end optimization. Yeah, for sure. So another question is, so considering the IoT environment may be dynamic, like the sensor locations may change over time, or the battery conditions are also changing. I believe, there are lots of uncertainty in the system. And also there could be some communication latency, right? So I just wonder, how does AI handle this kind of uncertainty and the real-time constraints in the IoT environment? Possibly the AI can also evolve over time, or some new system conditions can be put in the AI model. Yeah. So what kind of thoughts you can share?
Well, actually, if we need a very strict real-time interaction with the environment, for example, in many manufacturing situations or in some healthcare situation where the device is actually interacting with the person, since it's a life support for the person, actually we need to deploy on the peripheral the very simple operation. For example, we can deploy some signal and image analysis. We may deploy the controller for the local operation of the devices. How we perform the configuration of the controller? Well, this is not an activity which really need a real-time operation. So what we can do is to limit the complexity, moving the real-time activity on the peripheral, even if it's based on artificial intelligence, but leave the configuration to a higher level where there are more resources and the immediate response to the environment is not needed. So this will decouple actually the need for real-time operation from the learning part, which can be moved up. And the result of this learning can then be deployed again on the peripheral to have an update, to have a periodical update of the behavior of the peripheral. And of course, if we have situations in which the communication network become faulty, well, that is a problem. But if we have, since we do not have the communication, but if the critical real-time operation has been deployed on the peripheral in the Internet of Things model, for example, then even if the communication with the fog or the cloud became faulty and there is no way to reactivate it, we can continue to operate even if locally, even if the operation may not be the optimum. On the other side, if we adopt for the communication between the peripheral and the rest of the infrastructure some dynamic solutions based the ones that are typically nowadays in the wireless sensor network, for example, by using 5G or other type of solution like this, we may have an adaptive readjustment of the interconnection. And in these cases, what we can also do is to rely on the connection, the local connection between different devices, different Internet of Things devices at the peripheral, so that at least one may remain connected, so that we are channeling the data instead of directly to the fog node through the various other nodes which are nearby and available to the global infrastructure. And for this is important to limit a lot the amount of data that are transferred.
Wow, awesome. This is awesome. You have introduced so many different scenarios and different possible solutions and future directions. This is excellent. Really, thank you. Thank you very much. Yeah, I noticed you have so many research expertise areas like AI, computational intelligence, pattern recognition, system design, signal image, security, measurement system, industrial. So many. I just don't know how you can go deep in each area and combine them to have the unique research. It is really fantastic.
Well, I am not young. This is the reason.
Well, this is
And the trick.
all these are grand challenges. It's amazing. Okay. So if we do not have the quest, Douglas. Yeah, go ahead. Douglas is from BioCrossroad.
No,
the
no
venture
more
capital.
questions. No,
Go ahead.
my compliments. No questions, but my compliments. That was a fantastic presentation.
Thank
Yeah,
you.
for sure. Awesome. Okay, Dr. Puri, we will move forward to Douglas Kill, and then I will give also a brief talk, and then it is a panel talk. Okay.
Hey, let's see if...
Yeah, sure. Douglas, let me give the introduction of you. Okay. So Douglas Kill is currently the Senior VP at BioCrossroads, with the responsibilities including workforce development and chief technology strategy. So the BioCrossroads is actually a leading organization to basically invest in different companies and also to lead lots of efforts to lead the directions in industry and foster the collaborations. So it's really critical, organization. And prior to his current role, he served nearly 31 years at Eli Lilly and a company, leading the several global initiatives and support small and large molecular product development, manufacturing, and the CMC impurity control strategy implementation. And most recently, he established and led the Lilly's Global Transformative Technology Team, DT3, and the Digital Twin Center of Excellence, with focus on digital transformation, automation, among many. And Douglas Kill serves as a member of U.S. Pharma Packaging and Distribution Expert Committee, chair for the Product Quality Research Institute Steering Committee, chair for the Digital Twin Consortium Pharma Industry, regulatory working group, and executive governing council for the Nanobiomaterial Consortium. He also served over the last several years as the PHRMA topic leader and interim rapporteur for the RCH Expert Committee. He also serves as adjunct assistant professor in the Department of Industrial and Molecular Pharmaceutics at Purdue University. He has published his work in many journals and has organized, chaired, and presented at numerous conferences. Douglas Kill today will highlight the topic, exploring the digital event horizon, enabling digital transformation in pharma through cross-collaborative partnerships. And this talk will examine how pharma organizations are pushing the boundaries of innovation, not only through technology, but also through strategic cross-collaborative partnerships that drive real-world impact. Please join me in welcoming Douglas Kill.
Dr. Zhang, thank you so much, first of all, for the very kind introduction and also for the great the invitation to participate in this great event. And I just want to compliment and say I'm truly honored to be part of such a great panel this morning. And I want to thank all the speakers for the amazing presentations and inspirational discussions. So that's certainly, this is one of the best Saturdays that I can think of in a long time. So I really appreciate it. I'm assuming you can see the slides. I will assume that you can. I will go forward then. So a couple things up front. So this is a little bit of a different presentation, but I think it fits well with the order so far. And I'm really coming at this from commercial, pharmaceutical, and regulatory perspective. And a couple things up front. One of them is, what does cross-collaborative partnerships really mean? And Dr. Zhang, you've articulated that as well. But I want to indicate in the pharmaceutical industry, often because I have worked in other industries, I worked with, prior to Lilly, I worked with DOE, DOD, EPA on different initiatives, developing standards and guidance and some of the principles that guide those, some of those agencies and initiatives right now in the 80s. And often in an industry like pharma, and I'm sure others can identify, you have very bright people, but they're very pharma-centric, and they're trying to invent a wheel which may very well have been invented and perfected in another industry. So we have learned that we could really jumpstart and leapfrog by collaborating together with maybe industries that intuitively wouldn't seem like they would be natural collaborators. But we've really looked at a lot of different verticals and looking at those partnerships. Another thing is what's very different here when we're looking at really through an innovation lens and looking at implementing new technological approaches. There are three speeds at which commercial pharma operates. The first speed, which is really the fastest, is the speed of business. And then secondly is speed of innovation. And then thirdly, you have the speed of regulatory compliance. And that is the, if you want to think of that, that is the governor on the engine, because anything that is a great idea or innovative is not going to have pragmatic application and be able to influence the development and manufacture and distribution of therapeutic solutions to a patient population unless it meets regulatory compliance. So just very quickly, pharma has really lagged over the last several years, and this is a compilation of a few Deloitte surveys, and pharma hasn't moved much in the digital transformation in disruptive tool development and implementation. It's not, again, because there aren't very smart people or people who want to implement, but again, it is because pharma is slow moving, because change management, lifecycle management in a highly regulated industry is certainly not an easy task, because you have a lot of moving parts with the regulatory agencies as well as the industry to move that. So just a few bullet pointed disruptors for innovation in pharma over the last several years.
Sorry to interrupt. I'm not sure. Are you moving to the next page? It looks like we are still on the first page.
Oh, because I'm moving.
Uh,
Let
it's
me.
not it's not slideshow. It is the
I went into slideshow. Yeah. Can you see it at all?
uh oh yeah. So
Can you see
yeah
any slides?
yeah now I can see that. I can see the page 3. And
Oh, okay.
oh
Maybe.
there is actually I think there is slideshow in the bottom right, right? There the
Yeah.
bottom right.
Yeah.
Yeah.
And I was in slideshow.
Oh, I see. Okay.
Okay. If you're
Either
not
way
seeing
is
it,
fine. Either way is
oh,
fine.
okay. Are we? Yeah. My apologies. It might be.
No, it's fine.
Okay. Are you seeing disruptors, drivers for disruptive innovation?
Yeah, we are seeing page
Bullet
3.
points.
Yeah.
Okay. Yes. Very quickly. Thank you. Let me know if there's any other issues, and I'll just go to the thumbnail view. Precision medicine, patient-centric, tailored therapeutics are really driving kind of the next generation healthcare ecosystem and pharma engagement. Next gen cell and gene therapies, ATMPs, AI mitigated development, advanced manufacturing, digital twins. Looking at Pharma 4.0, the extrapolation of Pharma 4.0 or Industry 4.0 to pharma space. I'll talk about that a little bit. Additive manufacturing for potentially devices and smart oral dosage forms, wearable monitoring, sensing, smart diagnostics, integrated drug delivery. We talked about big data in some of the prior presentations. Also looking at limiting human interaction by implementing innovative approaches to virtual extended augmented mixed reality, particularly with on-site regulatory inspections. And again, I think everybody would agree here, certainly for my industry as an event, COVID-19 was probably the most significant inflection point that accelerated change, precipitated change, both industry and regulatory perception of risk, that being a key term, expediting innovative approaches for addressing unmet needs. So before COVID, it was inconceivable to think that you could abbreviate a traditional 10-year development manufacturing process to 10 months. So in terms of just some brief steps on digital organization and maturity roadmap for digital transformation. Most organizations transition from a pre-digital organization with hard copy based and manual operations, digital silos, islands of automation, some manual processes, the connected organization where you have vertical integration, some horizontal, electronic batch records, distributed automation, development of a centralized data historian, predictive organization, which is then the next step, looking at enterprise integration, integrating process development and manufacturing. And then the ring that we're all trying to grasp at the end of this is adaptive organization, where everything is end-to-end integration and at least conceptually everything plug and play. The ellipse that I have here indicates where the vast majority of large pharma resides right now because of the structure of large organizations as well internally with quality and regulatory systems. And so this is really where most organizations are on this particular path. This slide here, and I think
I have to interrupt you. Sorry, really sorry. We're still looking at page 3.
oh,
Looks
and I'm
like
on. I am way
oh
beyond that.
okay.
Okay.
Yeah, now it works. Yeah, page 4 now. Okay. Go
Okay,
ahead.
I've got a lot of animation. Maybe that's what's holding us up here.
Oh yeah,
So
sure. Okay.
I'll just go through it this way.
Yeah, okay.
So this is what I just spoke to. So this slide here, I think is critical with some of the discussion we had earlier, and I like this. This is really a view into what organizations think digital transformation is on the left, which is essentially implementation of a lot of IT tools and then claiming that you're digitally transforming. But digital transformation actually is an entire cultural change, which is very difficult for large traditional companies to recognize and adapt. And critical to this is adapting your company culture to embrace the change. And a critical piece is defining roles, responsibilities, and authority. So you have accountability. And there's this misconception that this is just, again, this is something that you relegate to your IT organization, and then they implement tools that trigger digital transformation without developing the infrastructure to not only develop it and to establish it and sustain it. So there's a lot on this slide. What I focus on only on is the left column. because these are some of the priority areas for pharma in regulatory science right now. The Pharma 4.0 to 5.0 concepts, which I'll talk about in a second. The FDA FRAME initiative, this is the priority initiative for the Food and Drug Administration for looking at rolling out conceptual advanced manufacturing scenarios to pharma for AI mitigated manufacturing. Some of this, the core pillars for this are end-to-end continuous manufacturing, which is probably the most mature with the generation of ICHQ 13 and the publication of that for international guidance. Distributed manufacturing, point of care manufacturing, and agile manufacturing. And then my organization that I chair, Product Quality Research Institute, has partnered closely with FDA on developing these concepts, and we're right now looking at scoping areas for standards and guidance development that would bring these to a pragmatic implementation. Digital and virtual twins as something that's very viable for end-to-end process automation, as well as tech transfer between development and manufacturing. As I indicated earlier, remote interactive evaluation using virtual reality concepts, smart automation, self-explanatory, regulatory expectations and standards. You can't implement again unless you have guardrails that are established by the agency and agreed upon by the agency. And then digital data quality and digital quality by design. Very important, because often solutions that are functional and when you press go, they actually work. It's an afterthought that the quality aspects of this, whether it's looking at deconvoluting and establishing interpretability and explainability and trustworthiness of a solution has been applied. So quality by design from the very beginning is what we've been looking at implementing as well. Very quickly here, for those that aren't familiar with maybe what Pharma 4.0 means and what Industry 4.0 is, there are generally this general description of the industrial revolution stages with approximate dates, but this all starts with mechanization, steam, water power, transitioning to electricity, mass assembly, factories, and telegraph, broad use for communications, turbines, engines. 3.0 is really the inception of computers, microprocessors, automation, initial robotics, digitization, electronic notebooks. The fourth iteration is where we live right now, and we're on the cusp of 5.0, where IIoT is really the defining term for this, with autonomous operation, advanced robotics, big data analytics. Digital ubiquity is a term I like, which is really describing this stage. And smart factories and a lot of these other concepts. And then 5 has a lot of considerations as we move towards what may be defined as overarching cyber physical systems and greater integration, understanding of how human and machine can integrate. So we're really achieving the best of both, as well as taking some of these other tasks that perform things much better than humans do, to take some of this off a human's plate and allow humans to innovate for the next stages of industrial revolution. Very quickly, Pharma 4.0, I just described what that is. Digital ubiquitization. Under this, if there's the animation here, ISPE, International Society for Pharmaceutical Engineering, coined that term based as an extrapolation of Industry 4.0 to pharma. And these are some of the core pillars for this, with looking at process maps, critical thinking, holistic digital enablement, plug and produce, developing AI, machine learning, and smart automation. Validating is and less complex but more effective validation is a very attractive proposition. Continuous process verification and process automation, with developing product release with parametric application. And then these are just some of the core pillars, very much driven at the bottom by the International Council for Harmonization, which I've had leadership on for the last several years. ICHQ8, quality by design, quality risk management, quality systems, and then lifecycle management for pharmaceutical products as being core on an international level for implementation of this framework for pharmaceutical digital transformation road mapping. Very quickly here, this is just an indication, illustration. Every couple years, regulatory science publications and white papers and discussion papers are put out by the FDA. And this is an example of one where they have emerging areas for regulatory science focus areas. And this is what my organization, Product Quality Research Institute, has actively participated in, working with FDI and scoping what some of these areas are, from drug delivery device innovation to packaging to manufacturing and other areas. And these are, again, I alluded to this earlier, some of the core areas for AI and advanced manufacturing, end-to-end continuous distributed agile manufacturing, rapidly reconfigurable, point of care manufacturing, which is very attractive but elusive proposition, either at the compounding pharmacy or even ultimately at the patient's location. And then AI ML application across the processes, some of the attributes or quality control, supply chain integrity, security, of course, supply chain re-onshoring and security vulnerability is a big topic. I was just in Washington last week for a lot of discussions on that with international contingent at the USP convention. Clean room, analytical technologies, automation, data visualization, pattern recognition, anomaly detection, being able to pull that out of large data sets, image analysis, predictive modeling and simulation, additive manufacturing. And I alluded to these earlier. The FDA frame priorities are end-to-end continuous. Ideally, where you're putting in starting materials and putting in reagents and other components for formulation, development of a end-to-end drug product. Ideally, this operates continuously, producing drug product very efficiently because of physics, first principles, things like computational fluid dynamics, chemistry. This isn't always feasible with all products, and it may be a mix between continuous and batch components of that process. Distributed manufacturing, very attractive because right now the construct is with pharma to employ contract manufacturing organizations or CMOs. That is because in certain geographies, China is a very good example. You can have a very effective product. China does not want to market that or approve that on their soil unless it is manufactured on their soil. So right now we may contract with organizations or manufacturing groups there for producing that. But the most effective way to do this is develop ideally identical and geospecifically or geo-advantaged locations for manufacturing facilities, and then you can relegate because all the componentry, all of the facilities, all the facilities requirements, environmental requirements, everything are consistent across those replicated facilities. You're able to relegate that to central AI control, and that takes a lot of that variability out of that particular construct. Point of care, I just described. A lot of these applications are additive manufacturing at the point closer to the patient, tablets, capsules, cell therapy, cell and gene therapy, prosthetics, and then delivery devices. Won't go through this. I indicated there were several publications, several initiatives that we've worked with FDA on producing. These are available from the FDA site, but it just indicates some of the trajectory for implementation of AI across development, manufacturing, and production of medical devices that the agency is beginning to explore. So if there's anything I'd say that somebody needs to know about me as a as a personal brand, I'm a broken record when it comes to digital twin. I personally believe this is probably one of the most promising enabling capabilities for product development and tech transfer and manufacturing process automation for the future. Virtual representation of real-world entities and processes or systems synchronizes specified frequency, fidelity, and you can accelerate holistic understanding of your process, optimal decision-making, effective action, decentralized, use real-time and historical data to simulate predicted futures, and it's tailored use cases guided by domain knowledge implemented in IT/OT systems. So it models a component, system of components or system of systems. The foundational principles for operation are either physics-based approaches like computational fluid dynamics or statistical approaches or estimated parameters. And this it should reflect as much as possible the operating asset, the physical assets, current environment configuration, tolerances, compatibility, material knowledge. And then this leverages operational data with predictive AI ML for optimized productivity, asset reliability, sustainability. This has a number of applications. There are different levels. This is just a subset of these. The digital model is probably more thought of as the simple model that replicates what a physical asset would look like. This is not connected or integrated with the physical model used for predictive and predictive functions and modeling potential scenarios, but in development. Digital Shadow has maybe one-way connection with the physical asset. There's process analytical technologies data to predict some process control, either at line, inline, or online. But there is an active sensing and actuation of the physical asset with a digital twin. The fully integrated digital twin, the virtual twin, is where the virtual asset, the model, is fully integrated with sensing and actuation at each unit operation level, monitoring those parameters, and being able to quickly mitigate any deviations or digressions that would take operation outside of predetermined specifications and parameters. So the digital twin enabling attributes, again, connectivity is critical. Physical sensing, actuation, the IoT, of course, having that bandwidth. Big data, all data is captured, as we were discussing earlier, aggregated and stored with multiple feeds, design specs, enterprise systems, and interpreted and fed back into lifecycle management to improve the twin with agentic function. Simulation, the twin operates either on simulation modeling, physics, mathematics-based modeling, as I indicated earlier, first principles, where there may be gaps and we need to zero fill. We'll look at data-driven modeling, analyzing system data to develop virtual sensors and virtual actuation until the physical is developed to discover relationships that we may not already understand from prior knowledge and prior operation of a particular process. And then the intelligence, self-descriptive AI, machine learning, analytics, having analytics workbenches to be able to interpret what data is generated and be able to extrapolate that into action. And then, of course, the actuators which respond to the sensing input. The value proposition here for pharma is I like this description here with the Rubik's Cube, where you can, of course, virtually perform thousands of simulations to solve a problem where it would take, of course, human intervention much more time to do that. But those of us who were kids used to cheat by just pulling the stickers off there and then putting them back on there when nobody was looking. But anyway, but virtually this is the value proposition. Then in a pharma product development, process development context, this is where this gets really exciting to a regulatory agency. Looking at applying your principles of prior knowledge, supplier information, process understanding, product into your quality target product profile, developing your critical quality attributes, developing your process map for each unit operation, whether it's fermentation, filtration, fluid transfer, filling. Understand what those parameters would be for that, developing your critical quality attribute assessment, your design of experiment, your analysis. Understand if your design space is okay with simulation for your process to ensure if the risk assessment is going to be successful, and then what you need to modulate to make sure that that risk assessment comes out positively. Once those risks are mitigated, you develop your control strategy and process validation. Why this is exciting is because all of this is very human intervened right now. This is physical process. So you're running validation runs by modulating parameters and producing product. When you produce product just to demonstrate that a run is valid, you may produce a liter or a kilogram of a product that is worth several millions of dollars. You're taking that to the incinerator or you're disposing that. And with multiple runs to validate, you have a huge sustainability impact, a huge cost impact, and time impact. So the idea that you would have a regulatory agency accept a virtual model, a twin, as the absolute representation of the physical asset, and then accept that you pressure tested that by running thousands of simulations with different parameter sets and show that the twin has an AI agentic mitigation that is able to keep that process in control through that entire process. The proposition is that you would have very minimal, if any, physical testing of product at the end, and that would be accepted as a validation with minimal material expenditure, and then potentially you would be able to release a product by showing that your process is in control through the entire product process without or with very, very minimal physical testing at the end. Very quickly, looking at some of the models that we've been looking at. This is just a general representation of a typical bioprocess that you would use for from cell culture to harvesting to filtration. This could be anything for developing peptides, mAbs, other bioproduct substrates and entities. And then this is an idea here of what this would look like. At the bottom, you can see we have each of the unit operations. For each unit operation, we would have developed physical sensing and actuation that would monitor critical parameters. And here I've got in these blocks just some indication of chemical composition or a chemical map. This is based on mass spectrometry in my case for filtration, in 2 cases, sterile filtration for fluid transfer, and looking at component interaction also with the process stream, and then looking at your last stage before your containment before filling. But this is just representative of each of the unit operations, and of course others in there as well, where you would implement sensing and actuation, and then these would be entirely mitigated and controlled, free of human intervention unless there's a physical problem that can't be mitigated by the twin, ideally. And the value proposition for time, for cost, and for consistency and control is huge there too. And so this is my final slide, but what we were doing was, in order to begin to inform this, is look at existing successful processes. These could be RNA generated, these nucleotide processes, siRNAs, or looking at peptides, looking at proteins, looking at MABs, looking at small molecule processes, and then looking at unit operations, all the prior knowledge, our materials of composition, dimensions, configuration, our compatibility, tolerances, process limits, conditions, our understanding of those operations, formulations, extractables, leachables, and then the value of the twin library is that we would now have maps of all of our processes, understand how we could take any of this knowledge, expedite our component selection for compatibility with future processes or similar formulation and process conditions, simulate, design, and assembly new processes, and then enable focus on knowledge poor unit operations rather than focusing on those that we already have much prior knowledge on. Facilitating trouble solution and failure mode analysis, and then speeding our process optimization validation, as I described earlier, which is a great proposition for the regulatory application within our quality parameter expectations as well. So I will stop right there. I wanted to go through this quickly. I hope I didn't go through too quickly, and sorry about the issues with the slides at the beginning. But I want to thank PQRI, I want to thank FDA for collaboration, also Purdue University, and I want to thank you for your attention. Thank you so much.
Awesome, awesome, excellent. You're an excellent broker for Pharma 4.0. Actually, you have highlighted lots of efforts or the possibilities in Pharma 4.0. That is actually my first question. Like, what are the differences, or what are the major directions, possibilities? It is wonderful to learn all these kinds of things from your talk. It is awesome.
Yeah.
Okay, firstly, let me check whether the panelists may have questions. Okay, Douglas, I have one question. You mentioned the innovation, and also you mentioned the regulatory many times. I just wonder, what are your insights on accelerating the innovation, given the regulatory requirements in the pharma industry, because there are really lots of regulations in this field.
No, that's an excellent question, and that is probably one of the primary key questions, which is it is because we have in the U.S. established a very and I understand why, but we have a very conservative risk and life cycle management curve for pharmaceutical products. So in other words, we have the extensive regulations we have because in our country we have a very low tolerance or acceptance rate for for products that have potential risk or for adverse events. Anytime you're introducing something that into your body that isn't part of your body, many people as patients don't understand that there is always a risk of it, some adverse event, because it is something foreign to your body, even if it has therapeutic effect. And so, looking at the level of regulation, and a lot of this based on clinical trials. Clinical trials are the probably the greatest expense in pharmaceutical product development and manufacturing. It's not innovation, it's not R&D, because clinical trials have to be large enough that they have statistical representation that that you can demonstrate you have less than 1 in a million adverse event rate. By adverse event, I don't mean death or anything even serious, but just some sort of an event that occurs with a pharmaceutical product. Now, there are other countries that have a different adverse event rate too, and it speeds products to market. But there's an acceptance of that risk. So I'd say what we have to do is really look at maybe our clinical trial structure, look at accelerating, some of our innovation, through that structure, and a different risk acceptance. And I'm not saying just throw all risk acceptance out the window, but we demonstrated we could do it. I mean, I presented at PDA and some other conferences before COVID on the concept of ultra rapid acceleration and manufacturing and deployment of pharmaceuticals to get things out more quickly. And I talked about abbreviating a 10-year cycle to a 10-month cycle. Well, people were laughing at me out of room, say they'll never happen. Well, a year later, this is 2019, we're doing it. So I think looking at where risk is essential or central risk parameters versus where risk is placed with certain testing and parameters, and the answer to the question is, why are we doing that? Well, we've always done that. Well, that's maybe not an acceptable answer all the time, but we need to take a very critical view of what are the essential risk focus parameters, and focus on those. And then what are some other things, maybe by therapy, it certainly can't be monolithic, and by patient population, where we can potentially accelerate some of this innovation to bring some of this into a more effective and expeditious scenario.
Yeah, awesome. Yeah, you're right. I mean, for sure, we have seen some successful cases which are approved quickly. Yeah, for sure. So, the BioCrossroads is a very reputable venture capital, and actually, lots of companies have been funded by BioCrossroads, and they have generated lots of benefits, and of course, the impact to the whole society. So, I just wonder, I mean, in the drug development life cycle, are there some specific areas where digital collaboration or the digital technology has the most immediate ROI, the return on investment, from your point of view?
Yes. So we see a lot of, and we've talked about some of that in this session as well. We see a really effective application at the discovery stage. At the development stage, so as we're looking from discovery through development through manufacturing, you have increasing levels of quality compliance and regulatory oversight. So I think what we're seeing is really that transition from discovery to development, and looking at, well, let me back up, because probably the stage one, where most things are killed that are very effective in discovery, a molecule that's effective against the target, is when it comes to toxin safety. And so I think when we're looking at how we can have predictive safety with parameters, and maybe look at molecule and scaffold interactions, and then have intelligence, be able to look at those and say, hey, this potential molecule based on it may be based on structure, functional groups, electron density, all of the things, quantum considerations, interacting with molecular scaffold, whether it be nucleotide or peptide or mAb or protein. Here are some considerations up front before we actually do the physical testing, where there's some prediction that there would be an incompatibility that could result in a tox failure or a safety failure. And we've actually been working on that. And it sounds like something where, most folks would think, well, why haven't they done that already? Well, it's not a very simple problem. I have a group that's overseas in Barcelona working on something like this right now, because it is quite a complex computational problem. So I'm going to throw that out to our wonderful panel and our people here as well, if anybody has ideas on that, because I would love to collaborate on it. And that is value proposition that would have immediate impact and return for the pharma industry for development into manufacturing.
Yeah, awesome. I believe, your expertise in Eli Lilly, and also your current leadership in BioCrossroads will make something really different and impactful. That is really awesome. Excellent. Yeah.
Well, thanks for your confidence. I appreciate it. I hope so.
Yeah.
It's fun no matter what. We're enjoying the road. Thank you.
Thank you. Whether we have some other questions? Okay, so okay, awesome. We have all the keynote given and there are lots of discussions regarding the exciting topics and also lots of communications will happen, I believe, after the event. Thank you very much for your valuable support and time. And based on the agenda, there should be a panel discussion. Well, we can talk freely, I believe. We have another 3 panelists, and they need to attend the graduation events. Right? This is not a good time. I have children. I should either choose the earlier time or later time. And they have, the school or department events they have to handle because one is the dean of the data science and one is the department chair of the computer science. And also another from Harvard, he's a physician and also lots of arrangements. So they have left, but they have shared lots of insights also. And we have the YouTube channel, which can be replayed. Given the time slot, I would see it will be great to further talk about, some new topics we together. It can be very, flexible and can be very, I would say, it's some kind of like the brainstorm or some kind of open questions and topic will be fine. Dr. Puri has been reputable in many areas and has been offering leadership in the IEEE for several decades. And Douglas has been combining the expertise in Eli Lilly, basically I think the largest company in the field right now in the world, and the expertise in the industry and also the current effort in the venture capital. I believe there are lots of opportunities there. So I have a quick question for each of you, and then we can have some open discussions. So Dr. Puri, I have as I mentioned previously, can you further share how you can combine and leverage so many areas and different fields to advance the research and innovation? I think it will take me forever to achieve so many things. It's really amazing. Do you have any insights or thoughts to share with us?
Well, actually, my research area evolved in time since back in the 80s, when I was doing my PhD, I was interested in VLSI design, high performance VLSI arrays for signal and image processing. And actually, I believe that attended one of the PCCC conferences back at the beginning of the 90s. That was in Arizona many years ago. And my focus was on fault tolerance. So I started from there, then I started being interested in the design of neural chips based on VLSI device, based on array processors. And from that, I started to be interested more on the theoretical part of signal and image processing and the neural networks for these areas. So from that, it evolved in time. And then at the end of the 90s, I've been focusing essentially on neural networks and in general, artificial intelligence. So my main research area nowadays is on deep learning networks, explainability, and their use in the real world, especially in industrial applications, environment, and biometrics. So basically, they are always the same aspect are different facets of the same problem. So this is why in that case it was easy actually to expand the research in these different areas. And then of course I had also several collaborators who helped me in better understanding these topics, and working together we have been able to address these different facets. Since what I believe that is important in research is that and both of you, I guess, agree, it's important not to be only on the theory, which is nice, but also to see how it can be really used. And I believe that it's important to get ideas from the real world, challenges from the real world in order to improve the theory. Otherwise, sometimes it may remain too disconnected. And I believe that this is useful also for the young professionals, since this kind of balance between a deeper understanding of the theory of the methodologies, coupled with a look to the application and an understanding of the at least one application area, will be very interesting, in my opinion, also to create new startups. And as a consequence, not only to advance technology, but also to contribute to the economic development. And this will be very important more and more around the world to increase the level of the economy, as well as to provide an opportunity to contribute to increase the quality of the life of people around the world. Since many of the achievements that we have now in biomedical, in automotive industry, they really help in improving the quality of the life at the end of the day.
Yeah, awesome. I mean, all these are very critical insights. Like you mentioned, actually, it is really important to find out the common factors and also the differences from different approaches and different areas. I would say only with the expertise you can see this kind of high-level abstraction or high-level philosophy. This is not easy, actually. This is really fantastic. And also you mentioned the combination of the research and also the the practical applications, right? That is really to maximize the impact of the research. That is awesome. And also lots of great suggestions for the young professionals. Really awesome. Really thank you for that.
Okay.
Yeah. Douglas, I know, you have the expertise in Eli Lilly, and now you're working in the venture capital. Can you share your insights, like what will be the critical thing to maximize the return and minimize the risk? Oh, you're muted.
There we go. Yeah, it's
Okay,
double mute. Yeah.
sure.
And no, great question. And so to frame it though, I've only been in this for 4 months. So I BioCrossroads, I'm very new to this. And my goal here has been, of course, and it plays into this as well, is workforce development, to look at bringing in workforce development from early, even from high school on through community college and advanced degrees, but look at technological areas where we can enable a workforce to have the skills to bring some of these things that are, and Dr. Pieri, I really appreciate your comment on how theory can be great. It can be a great concept, but unless you can demonstrate practical application and it really impacts somebody's life, it's not going to get much beyond the theory. And so, and then same as being able to develop something, but having it really developed in a very narrow area, and you don't have a workforce that can take it and has the expertise to develop it. So that's one of the areas I've focused on, as well as looking at frontiers for emerging technologies. And so for me, I see a lot of, well, I did this when I was with Lilly before too, and a couple of weeks ago I was in Arizona, Phoenix. Since I work with SEMI, we had a really nice workshop on the future of electronics and smart medical technologies, which is very, very much aligned with what we're discussing here. And a lot of we had a lot of innovators there, much as we see in the venture capital space. They come in, they have a great idea. Maybe they have something, it's a novel synthesis, or it's a novel way to develop very effectively a new advanced therapy medical product, which could be commercialized. But having the appropriate, I think the appropriate network and framework and discussion to be able to inform them as to what the challenges are and the barriers they are going to face, and what skills and partnerships they need to bring that forward. I think that's a big piece. And often I was brought in, when I was at Lilly, as somebody who was an expert who could inform because I have the regulatory, interaction and lead with the FDA. So I could tell them, hey, if you're bringing a device forward, this is what CDRH expects. You need to understand what biocompatibility is with your material selection, all these different things, before they get to a point where a really good idea has stalled because they don't have a path forward, and they get discouraged with that. So I think having that appropriate network, having that structure, to be able to say, hey, we're going to not only encourage you to continue developing and advancing your great idea, but we want to bring around you partnerships that can lay out a viable path forward to bring this to the attention of people, and companies that could really use it, and to get it in front of individuals who can advise and inform for where it's needed for regulatory path forward. That's where often I see a lot of these stall. They're in that innovation space. And they've got a very narrow group that's working with them. But the question is always, hey, Doug, how do we get this in front of the FDA? How do we get this to the next step? So I think how we would develop and convene that through consortium opportunities or collaborative opportunities, I think that's a structure that would be very helpful.
Yeah, awesome, awesome. I would say, you have mentioned so many aspects. I believe I would say you will easily find the optimal solution to basically combine the capital, right? The team and the technology, product design, the market, and the talents, everything together. You have covered so many different things. It's like the NP problem. It is really difficult.
It's very difficult. Yes.
Okay.
You do a lot of influencing without authority, which is very difficult.
Okay. Yeah. So, I have some kind of general question, like so in practice, how hard is it to move from the proof of concept to real world impact, and what factors may basically slow down that process? I would see whether both of you can share your insights. Basically, how to convert the concept to technology, or to the products.
I'll start with just two words, and and Dr. Pieri, you alluded to this as well. And I alluded to this earlier in the discussion. The two words are use cases. If you can develop use cases that show return on investment, show how this concept is actually functioning in an operation environment, it's much easier to bring that forward and get somebody to buy into it in a commercial environment. I'll stop right there.
Well, you are perfectly right. But I believe that also you need people like you who can guide the process for people who may have some technical insight, but have no clue how to identify a business case, how to write a business plan. So for this reason, I believe that is really important to be able to have the support of incubators, industrial incubators, or mentors, venture capitalists, group of people like this who can help during the process.
Yeah.
Since if someone is working in research, even if applied research with companies, is focusing on the research part. And then the development of the real solution is typically carried out by people in the company. Having someone who is young and would like to create a startup, they may become fluent in a specific technological area or application area, but then need actually help to build everything, to put together everything in order to make good proposals, get sufficient funds, and be successful. So it's not something, in my opinion, that just pop out of the blue without appropriate nurturing and mentoring.
Yeah, really, really great points. I think these are really key considerations because if we look at startups, right, most of the startup may unfortunately fail over time. But if all these kind of considerations can be, I would see, playing some critical role, right? That could possibly increase the success rate. This is really challenging. Sorry, it's a little bit noisy outside. So, uh, can you possibly share your insights? Like, what are the hard technologies, really hard technologies, in your field or broadly in the industry?
Well, for sure, technologies in artificial intelligence in general, uh, especially nowadays, the natural language processing, which is a field um, capable of supporting the analysis of documents and interaction and extract some knowledge, will be more and more useful in a broad variety of applications. Um, Other areas, for example, communication technologies, the more advanced communication technology, 6G and beyond, will be very important in order to ensure a connected world. Especially when nowadays we have so massive amount of data that need to be exchanged and transferred in the network, having very efficient technologies for communication will be very, very important. And I believe that this brings also on the table another topic, which is the security, the privacy, the protection of data that are flowing in the network. Since these are more and more important, the more critical is the application, the more the protection of the network of the data becomes important, especially when we are connected so much, when we are on social networks, where we may want to share some information, but also there are challenges, and we may not want that some critical data, our biometries, our face, for example, are misused for other inappropriate actions.
Yeah, for sure. As you mentioned, I mean the AI model and also the data and also security. There are so many different aspects. They're all together will advance the practical application for sure. Uh, yeah.
I completely agree with that, and
Yeah.
that was going where I was going to go as well. Because again, just coming from the conference a couple weeks ago, with the electronics and smart medical technology, bringing semiconductor innovation together with medical technology, smart technologies, enabling more patient-centric but also accessible, and which Dr. Piri and Jack, this goes to what you're just discussing as well, which is the more convenience that you offer through the connectivity, that, as you indicated, absolutely correctly, is the greater the concern for the security. And so you do come into this balance where you have patients say, I want that remote connectivity, accessibility, immediacy, expediency of the care. But wait a minute, I've also got privacy concerns. So how I think there is and the payer relationship as well. So how do you fund a lot of this, and how does the patient fund this? Or how are the healthcare organizations funded through this as well? So there are a lot of moving parts here where, from the patient population, sometimes there's a realization, oh, I got to be careful what I ask for, because now I'm revealing a lot of information into a network that I don't know much about myself, and trusting it. So so I think there's that balance has to be achieved, and it has to be communicated to the patient populations, particularly with smart healthcare, about the trustworthiness and the security, as you indicated, of that information, or else all the innovation can be as attractive as possible. But if those vulnerabilities exist, again, we're looking at that right now. The big discussion right now, as I indicated when I was in Washington last week, which is also cybersecurity, information security, is the whole supply chain vulnerability and reshoring of that because of all of the critical supply chain components in any area, whether it's pharmaceutical security or it's food security or environmental security, a lot of other things. So I think the more that we have the connectivity, which is absolutely where we're going, that train is out of the station, it's not going to stop, and it's beneficial to us. But it does the technology advance more quickly than the appropriate, and I hate using the word control, but the appropriate cautions and protection mechanisms around it, that make it safe to use for different areas, and trustworthy. Is that going to be developed same time? And that's the value proposition with looking at implementation of these technologies in the pharmaceutical environment. That's why it is slower, because you do have the FDA saying, hey, we're responsible for anything you're implementing. You release a product with an AI mitigated process, and you don't know what those algorithms entirely, are doing. What if there's a hallucination? Now, the FDA gets the, gets the punch in the nose for that. So, it's I completely understand. Kind of digressing there, but I think it's relevant.
Yeah, for sure.
Yes, and thank you for having brought these aspects on the table, since I believe that also is very important to increase the awareness of people about the technology, the awareness about the proper use of the technology, since this will help in having no fear about the advancement of technology, but will help also in understanding how we should use properly the technology, the advancement of technology in the real world, which implies to have a better understanding and good care about the legislation that may guide and prevent possible critical situations. And on the other side, I believe that it's important to favor the education of the professionals in the area of ethical use of the technology, since these new technologies may really make the difference in a positive way in the life of people, but we need to ensure also that are not misused in the application. How many people, when they go in social network, have no clue what is happening about their data, and they share everything, and then after maybe 10 years, they think that they may have not shared everything.
Mm.
Yeah, absolutely. I would say, there are lots of, considerations in the AI model design, technology development. For sure, as you both mentioned, the AI system needs to be, stable, reliable, tested. Like it, I think it needs to be scientifically valid and practically reliable, especially for applications like smart factory, medical, and some kind of autonomous driving, and etc. Right? So all these have actually very high requirements on the reliability, and also the basically it can handle different kinds of uncertainties, whether data set is sufficient enough, whether data set is covering some like kernel cases, or whether it can make mistake, even the probability is low, right? All these are actually very difficult, I would say, engineer and research works. But I believe the whole industry is making lots of efforts. If you look at the big companies and the middle-sized companies, startups, all these kind of massive efforts are in this area. I believe this will be fantastic future for sure. So can you both envision like in 10 years, right? I know this is not some exciting question. Maybe for all the panels there will be this same question. Like in 10 years, what kind of critical technology or capability do you think will be achieved?
I'll just say quickly, for me, I can't imagine 10 years. And I've learned over the last couple of years, and I'm sure you both can agree, I couldn't predict what was going to happen 10 months ago. So, I even 10 days in some cases. So I think if I'm looking just what's going to happen 10 months from now, there are probably significant things at the rate things are developing right now that are going to occur. I couldn't even imagine. I can imagine, but I think it would be difficult to predict uh, uh, with some of the unforeseen things that have happened. What could be 10 years. That's just my own view.
No, I agree. It's pretty difficult to predict the significant changes, but I believe that the research in the area of quantum computing, for example, will help to give us tools, systems which really may speed up many of our algorithms, and as a consequence, many of our applications, which now are almost unfeasible due to the amount of time that is needed. On the other side, I believe that if we look to the research in physics, we may get more insight on the nature of the particles and have a better understanding of opportunity to exploit this knowledge in order to produce energy at a much lower cost with much lower impact on the environment. And since basically energy is what will help any type of activities and spread any type of activities around the world, improving the quality of the life of people. Since in order to be connected, we need to have the energy. Solar energy is a good solution in rural areas, but may not be enough if we wanted to have many more other type of applications. Think, for example, to precision agriculture, to medical application with a continuous monitoring, or any other type of application. In this area, we require to have sufficient energy to support these activities. So I believe that these will be definitely areas in which the research which is carried out in the major research centers can make the difference. A better understanding of the different material will help building new products, new material. So, and the creativity of people.
Oh, sorry, Dr. Perry.
No, please.
I completely agree. That was fantastic. I just want to add to that. I think also, all kidding about 10 months aside, even though I only half kidding. For me, it's looking at, what I spoke about earlier, the Industry 5.0, really cyber physical systems, cyber physical integration. On the defense side, that's looking at human performance enhancement. That's very real. But on, the practical side, there are some promises that we've seen for this technology to reverse or completely alleviate the effects of serious disease states like Parkinson's, or one of those that's so elusive that would be a huge win for us would be Alzheimer's. So how we can take these technologies and potentially cyber physical integration, reverse the effects of sight impairment or hearing impairment, or or even enable mobility where there's a disease state that is completely removing somebody's ability and enable and taking away their ability to be independent. So these are huge value propositions, I think, that are really within grasp right now with some of the things we've seen as we understand the brain, as we understand some of the neurological aspects of this, and how the integration of some of these systems could potentially enhance and really improve, Dr. Perry, as you said, improve improve life and health, and that's a big one that I'm very excited about.
Yeah, surely. I would see like you both mentioned, and also Dr. Puri at the beginning mentioned that the critical research, right, and the human resource, the center-based research, etc., will for sure I will see advance the possibility and increase the possibility of success or the practical application. And there are also lots of surprises, right? So if we look at the drug targeting the diabetics in Eli Lilly, it has found new function. Then it contributed a lot to the human health, right? So this is some kind of unpredictability. So, but also big surprise. Yeah. Okay. So, so in future, the technology will be advanced, continuously. So what will be the role of the human subjects, the human people, right? So how should we balance the human expertise and the machine insights in the decision making, especially like in the autonomous driving, medicine, or the science or drug, whatever. So what will be the role of the human in this kind of decision making process?
I'll just give you a quick thought from my end, because I've had this discussion in several groups recently, which is I think there is I don't want to use the danger, but risk in our relying so much on this intelligence, on AI, and these the advancement of these tools to think for us. I think we're giving AI, people who don't understand it much and realize it's just a tool. They're giving AI a mystique that it hasn't deserved or earned. So I use the analogy that if you brought a Makita power drill into King Arthur's court, it would be viewed as sorcery and magic. I mean, AI, some people are viewing that much the same way, as it is going to be this amazing problem-solving tool. And I would hate to see the brain can still do things, and the AI, the agents we're developing, the tools we're developing, they're still developed by humans. They're based on human assumptions. And so, the danger is if we say, okay, I don't have time to think about this problem. I mean, there are things that are rules-based activities. That's fine. Just routine activities. That's a great use for a lot of these tools. Or to say, let me give you some idea about possible routes to take for solving a problem. That's great. You're using it like a good screwdriver. But if we've got people, particularly in positions of leadership, regardless of the industry, and they're saying, I don't even need to do anything anymore. This agent is going to think for me. I think that's where I would be concerned if we have that much reliance on some of these technologies, and kind of and overlook the fact that these were developed with human bias and human intention, and that we completely disregard human intervention and the human piece of this as well. So there's just my own thoughts.
No, fully agree. Fully agree. Since I believe that, as I said before, having an understanding of the technology is important, but it's important also to be aware of a proper use of the technology, of an ethical use of the technology. And personally, I believe that, as we have seen in the past, and will be the same, in my opinion, for artificial intelligence, artificial intelligence will not be able to be more intelligent than humans, since it is our artifact. We are creating that. I believe that anyway, humans will be in control of the artificial intelligence techniques. And as a consequence, what is important in order, I mean, we can use the artificial intelligence to try to find a solution, to explore possible solutions. That is perfectly fine. But we are going to choose how to solve the problem. We can base our decision on what we are able to extract from the knowledge available worldwide provided by artificial intelligence. But I believe that what is essential, and we need to teach this to the young generation, is to maintain the critical thinking approach. People need to always to think in a critical way to understand what is true, what is fake, and not just take everything as a true. And this is one, for example, of the big problems that we are facing nowadays in many areas.
Yeah, for sure. As you mentioned, it is important to explain the behavior of the AI model or understand the learning principles, like at the mathematical level or the abstraction level. So I want to end the event with the last question. I just wonder if you could magically solve one problem with unlimited tech resources and talent, what would you tackle next? What will be your first choice? What will be the most exciting thing?
I believe that trying to have the best technology, helping medical applications to be as much effective as possible is one of the important opportunities around the world to benefit humanity. So I believe that this is an area in which we should continue to invest. But it's not just technology. I mean, is any like computers or artificial intelligence is any kind of technology which may help people to live better is essential, since technology is important, but having the human as a center.
Yeah, for sure. Totally agree.
I couldn't agree more. That was what I was going to say as well. That's I think that's absolutely, far and above. And especially, any of this technology and the applications like that available to populations everywhere, whether they're in countries that are prosperous or they're underserved communities. Having that level of availability, so there is no privilege associated with it, but absolute accessibility. So the benefits can be realized. Secondly, I'm thinking in addition to all of the health concerns and being able to alleviate disease or reduce incidence of life-threatening and life-altering and changing diseases, but also if this technology would be able to come up with solutions to increase food security and increase availability of food supply to countries that are living with that challenge every day as well. That would be a great application of this, when we're looking at agricultural, applications of, some of the novel technology we're looking at implementing in different ways. So that's another one there that I think it goes hand in hand, or it's right up there as important as the healthcare in my mind. But those would be problems I think I would if I could wave a magic wand, I'd love to see a solution for today.
Okay, awesome. I really learned a lot from
Really.
all your insights. Really, thank you. I would see it is the time we can finish the event, and really thank you again. Appreciate for all your support, for your time and for your insights for sure.
Well, thank you. This
Thank
was
you
an
for
honor.
having organized this event. Thank
Okay,
you.
Yes.
really thank you.
Yeah.
I wish
Look,
you a wonderful summer, upcoming summer.
same to
Okay.
you.
You too.
Look forward
Okay.
to a future event. Let's do this again. Okay.
Yeah, for sure. It is great. It is a great opportunity
Okay.
to really share the insights and really learn, from different aspects, because you are all very, I would see, as I said, you are all standing at the edge of the innovation practices, applications. This is really fantastic opportunity to have this kind of event with your support. Really, thank you.
Thank you so much.
Thank
Okay.
you.
Okay.
Okay.
Bye,
Thank
everyone.
you.
Bye. Bye,
Yeah,
everybody.
bye.